Good afternoon and welcome you all to the second Thailand ACPE Forum, Disaster Insight, Lessons Learned from the Recent Earthquake Impacts on Engineering Works in ASEAN. I'm Nahathai Jaikla, very honored to be the MC for today's event. As we all are aware that the world is now changing fast and extremely in some cases, we witness more frequent and more severe disasters, such as the recent earthquake in this region. This incident called for the Council of Engineers Thailand to initiate a forum to share experiences, facts, and standards from the engineering practice perspective, hoping to improve the engineering standard for future disasters that may happen. So before we dive into the interesting topics after this, I would like to invite Associate Professor Dr. Quanchai Leepowpanth, the second Vice President of the Council of Engineers Thailand, to share with us the objective of the forum. And please welcome Dr. Quanchai.
Ladies and gentlemen, my colleagues from ASEAN countries and other countries. We have today over 500 participants from 11 countries, including 8 countries from ASEAN. The remaining from India, from Japan, and others. I thanks for all participants and interest in listening to our second Thailand ACPE Forum. In the past 3 months, we had this incident, the earthquakes in Myanmar, a long way from Myanmar to Bangkok. And there was one of the buildings, high-rise building, during constructions, being collapsed completely. This is interesting. And this is the reason that we hosting this ACPE forum today, this afternoon. The committee for investigation of the cause of building collapse was appointed by the government. And by the end of this month, the next Monday, the result from investigation will be finalized. Today we are able to present to you all some facts about the effects of this disaster, and also we are trying to discuss if we could do something together among ASEAN countries to save more lives in the future. And actually, today's forum is not solely initiated by Thailand. We had a discussion among our ASEAN friends, including Engineer Andy, which I like to name him. We discussed in what apps, and this is, for example, you can see in a screen. Engineer Andy set up this ASEAN disaster seminar group, discussion group. So a few members, expert in disaster management and disaster resistant design, code and standard, are in this group, and we discuss. Thanks to Mr. Andy from Indonesia. In this group, we discuss about the earthquakes in Myanmar and Thailand. And someone raised the question that how could we do something to something like this. Someone says something in a group. Is there an idea what we do to give purpose to this group? And someone also gave a discussion. We can make a discussion in kind of webinar about what happening during earthquake and what caused it and what should we do to prevent such things in the future. We just replied that that's a good idea. We could organize a joint webinar, online seminars to share experiences on disaster management and earthquake resistant building design standards among Asian countries, something like that. The discussions going on, and group members agree the need to share lessons learned from the recent earthquakes in Myanmar and Thailand. Asian member states should share experiences on earthquake-resistant design, construction practices, building permit and processes, other earthquake-related disaster risk reduction efforts, something like that. And then we agreed to organize this forum as a ACPE second forum, and Thailand offered to host this forum today. We have the objective to share lessons learned from the recent earthquake disaster in ASEAN, particularly from Myanmar and Thailand. We should exchange experiences on earthquake-resistant design, construction, building permits, risk reduction practices among our ASEAN countries. And then we could discuss practical measures to enhance earthquake disaster risk reduction across ASEAN countries. These are objectives that the group agree to organize this forum. And today we have the privilege from the Deputy Governor of Bangkok Metropolitan to share her experience on the recent earthquake disaster management. And she was there from the first hour of the earthquake until the last day. And she saved a lot of lives. So thanks to the Deputy Governor of Bangkok Metropolitan. Apart from that, we have the expert, Dr. So from Myanmar, to share experiences and information from Myanmar. And also two other experts from Indonesia to share their experiences in Indonesia. It's a pity that some experts from other countries like Japan could not come today. And we also have one of the experts in Thailand to give us some facts about what happened in Bangkok in the past 3 months. So this is the objective of the forum today. And I hope you that participate in this forum would benefit from the discussion, more or less. I hope the discussion and presentation in the forum be going well, and I'll be with you until the last hour of our forum today. Thank you so much.
Thank you, Dr. Quanchai, for sharing the forum's objective with us. Now I would like to invite Associate Professor Dr. Thanes Weerasiri, the President of the Council of Engineers Thailand, to give the welcoming statement. Please welcome Dr. Thanes.
Dear speakers, guests, and friends, welcome to the second ASEAN Engineer Forum 2025. Today, we come together to learn from recent earthquakes in our region. These tremors do not respect borders, so we must stand as one to keep our community safe. Over the next few hours, we will look closely at what went right and what went wrong. When the ground moved, we will hear data, stories, and new research on shared in clear, practical language. Our goals are simple and joint. 1. Share hard-won lessons from the latest quakes, so no country needs to repeat the same mistakes. 2. Join hands across ASEAN to apply strong and common building rules that save lives. 3. Keep learning so every engineer in cities, towns, and villages can protect people and property. 4. Explore new tools such as digital twins, real-time sensors, and low-cost retrofit methods that fit our local needs. Friends, today's forum is online, yet our mission is hands-on. When we log off, let us carry these ideas back to our offices, our sites, and our classrooms. Together, we can raise the strength of homes, roads, bridges, and schools from Myanmar to Malaysia, from Laos PDR to the Philippines. I thank our speakers, the ASEAN Secretariat, our organizing team, and every participant for giving your time and talent. Your ideas today will shape a safer, stronger future for more than 650 million people. Please enjoy a fruitful forum. Thank you. Thank you very much.
Thank you, Dr. Thanes, for a warm welcoming speech. The session following this will be a presentation from the speakers and panel discussion. So during this session, if you have any question, please drop it in the chat box and our administrative team will display it for the speaker to answer your question. So next on the agenda is going to be the experience sharing from someone who was in charge of the disaster response in the new state audit office building collapsing incident. We have the honor from Associate Professor Tavida Kamolvej, the Deputy Governor of Bangkok Metropolitan Administrative Office, to be our keynote speaker. Dr. Tavida will be presenting the best practice effective disaster management in the recent earthquake in Thailand. Please welcome Dr. Tavida.
Okay, thank you for inviting me to this seminar and conference. And I happen to run into Professor Thanes for quite some times because we work together also on the latest earthquake that happened. From what I see, let's say let me go by chronological a little bit in terms of what's going on and what else that I can relate to the engineering part of it, because let me make my excuse first that I'm not an engineer. So anything that I say is wrong. Sorry. On that day, I think there would be some problem, and that problem gonna be continue on until now today. First of all, is that in that particular moment, that when the earthquake happened, of course, it's like taking 5.5, about 5.5 minutes to come to take impact in Bangkok. I argue. A lot of people said that the Thai, they don't know that they have to stop, drop, take cover. I argue on that point because even me, I actually stop, drop, and take cover already. But there is a huge but. I think in deep of our heart, subconsciousness has been working that how much we trust the building. And how much we trust the building, it has nothing to do pretty much on only engineering part of whether or not our building built on what year, and that year the building code has already been in place or in the act yet. I don't think that's what it is. I don't think that's only that. Because even the engineer also mentioned that even though we just launched a parameter for an earthquake resistance to the building, but it's just several years ago. But the building that is older than that, it doesn't mean it is weak. So I think when we said people don't trust citizen of Bangkok here, they don't trust the building. I don't think the answer is whether or not we have parameter of earthquake resistant solely on that one. No, I think it because we are not sure if it is very old building. We don't have knowledge enough. We are not engineer, and we know that aging structure also somehow degraded, and somehow it might not be that strong. That check one. Second, even if we know that the process, the law control the building, it doesn't mean that the building is actually built in such a way. I think this is a trust toward how we actually make how we build the building. Um, Thank you very much. You might have to go down and find the slide said Bangkok roll in earthquake. It will be far at the very end. You can keep going. I'm gonna keep talking, and people move. I think that when people move during an earthquake, it will be several slides. Ka. I'm sorry. Anyone that putting the slide for me, it would be far away from the beginning. It's gonna be almost like at the end as a huge slide. Um, can you move just a little? Um, yep. Go ahead and you move until you see the word Bangkok roll on a green background. Yes, Bangkok roll on earthquake. I'm gonna keep talking. On that day, when we moved out of the building, this is what Bangkok actually did. We assemble our EOC and still going ค่ะ It would be after flood ค่ะ Okay, thank you ค่ะ Then continue to the next slide ค่ะ on that day when we heard the news of the building collapse, you have to. This is what I don't know. What should I do in the next years to come or in the near future? I need to control a little bit more on social network, not to forbid them to post anything, but I have to be the one. อย่าเพิ่งเลื่อนค่ะ I'm sorry. โอเคค่ะ ขอบคุณค่ะ I have to be the one that perhaps sending out the news to compete with the new in social network. That's the other thing too. You know, when people don't trust, subconsciously you don't trust whether or not your building is strong enough. Even if you already go down there, stop, drop, take cover. And then even if you know, I know I study from all the professor as well, like not officially. But when the building shake that much with that long kind of like minute, you can't do anything. People will run anyway. So when people run, and then the picture of these slide is actually on the internet and social network, you can't help. People are gonna actually move from the building, or even the building stop. Even if the building stop, even if the aftershock that come afterward, it doesn't actually impact the shaking of the building. They're not gonna get back because of this picture. No one is gonna actually trying to understand that, okay, Bangkok has about what, 6,000, 7,000, 10,000 buildings. None of them collapse, only one. No one is going to try to understand that we have about 210 sites of construction, only one collapsed. Some of the cranes actually broken too, but that's fine. Anyway, I think we are somehow outrun by all the information that flood people and that subconsciousness of thinking, trusting the building or not. That check one. Unfortunately, the hospitals as well. BMA supervising, controlling 12 hospitals on its own. For those of you who are not familiar with Bangkok, Bangkok has about 160, 70 hospitals. 21 belong to public, 12 belong to Bangkok administration. Every hospital of mine, the director of the hospital evacuate even a critical patient. Lucky us that none of the patients actually have severe damage, severe in terms of symptom or die. No, none. So it's lucky us. I be able to move them back on their ward at 5 o'clock in the evening, about 3.5 hours after the impact. Before moving them back, BMA sent their own engineer to each of the hospitals that we supervise, also the other hospital that we don't supervise, trying to help to evaluate, preliminary evaluation in terms of whether or not you can go back. But back in that certain minute, we already know that only one building collapsed. We already know that only one building collapsed. And we also going out and check. And we also know that mostly is cosmetic damage. Or the damage that in engineering code is a yellow one, in which it's non-structural damage. It's not a structural damage. Lately, when we do a very deep examination, only 2 of the residential area private building that was tagging red and requiring a retrofit so that people can move back. So that's the situation. We then separating the work into 3 different areas. Physical. Next slide ค่ะ โทษทีค่ะ Can you move next slide? Thank you. This is a timeline though. I'm just giving you a timeline. It's going to be really a lot to digest. So I'm going to try to give you a certain period of time. The most difficult is the first 24 hours in not only on the site that building collapse, that will be a chaos for another 48 hours, pretty much like anywhere around the world when this happened. 24 first hour would be the hour that we set up the site. All the engineer has to go there so that we know that the rubbles that come down from 137 meter, that's the height of the building, 30 floors, or 137 meters. When it came down, the height of the rubbles is 26.7 meter. With the pancake pattern of collapsing, you already know that. One of the most difficult collapsing pattern ever for search and rescue, much like me. And that's, we busy on that one. And also another 49 districts. Bangkok has 50 districts, 50 districts. District that has building collapse, only one district. Let's set it aside. The other 49 districts also feel the shake. Everywhere in Bangkok feel the shake. And has a different kind of damage, mostly cosmetic, as I said. For the first 4 days, we opened the application fondue. Move ได้ไหมคะ move slide please. ค่ะ another one มันจะมี this is an EOC that we set up. I'm gonna get past a little bit quicker in terms of the EOC so that okay. Another one, I will come back to this. I try to have the one with ฟองสไลด์อีก1อันได้ไหมไปอีกอันนึงค่ะมันจะมีฟองดูอยู่โอเคค่ะกับซ้ายค่ะกลับค่ะอีก1อันค่ะ back ค่ะมันจะมีฟองดูอยู่ด้านซ้ายค่ะ back อีกอันสิคะแล้วจะมีอันที่เป็นแอปพลิเคชันฟองดูอยู่มุมซ้ายอะค่ะอันนี้ไกลไปแล้วค่ะว่าอยากเปิดเองอะyou stop thank you ค่ะ if you look at the left hand side of the slide, this is the application traffic fondue that Bangkok's already implemented since second week of our term. So we've been using that 3 years already. And on that day, we know that people who stay in a high-rise building, especially condominium where they have to sleep at night, We also know that they are going to be too scary for them to go home. They don't trust the building per se. So the way that we can comfort them, one of that, we open the Fongju, your left, upper left, I'm sorry, it's in Thai. The upper left under the speakerphone, Fongju, that spell out in Thai is a crack in the building. So this application, basically, if I explain you Fongju, it's actually from Thai word though. Complain to me, complain to Bangkok administration where the problems are. We use this in a routine mode, public service and everyday problem. But this time we open the new button, new module, which is a building crack on that one. You can just get in, take a picture of your room that have the damage or your building that your resident area, and then send it to Fongju. We have a volunteer of an engineer coming to our EOC to help looking at the picture whether or not the damage is more or less, and we communicate it back to the people that your room is fine, your building is fine, it's a green tag. So with all this, as you can see the number through Fongdu system for the past event, we get about 20,000 complaint that there is a crack in the room. These 20,000 ended up about 5,200 buildings around Bangkok residential area. With this 5,200, we sent out an engineer, thank to the engineering and also the engineer association that invited me today. Because of you guys voluntarily get together with us, like 200, 300 of you coming to help Bangkok to go and do the examination of the building so that we can answer to the residential building that is safe to get in. Roughly with that 5,200 buildings, only 2 have a red tag. It means retrofit before going back, structural damage. 250, 5% of a 5,200 is tagging yellow. It means that it's a non-structural damage, safe to stay and use. However, the owner of the building have to call the engineer who actually the examiner to investigate the building as soon as you can so that it makes sure and have people give people a serene mind that they can stay on put. And the rest of them, almost 5,000 building off of a 5,200 something buildings are tagging green. It means of a cosmetic and hairline damage. So these also in disaster management, you don't wait until each of the step finish. For example, pre-disaster prevention, mitigation, preparedness. During disaster response and relief. Post-disaster, in which is early recovery, rehabilitation, reconstruction. We don't wait for each step. It's not linear. Disaster management is non-linear. So as the time that we still respond to the situation of the building collapse, we also managing what I call both response and early recovery. We are actually trying to calm them down that they can stay. And anyone that is not trust enough, just want to wait for a little longer hour, you can go to our park. We open the temporary shelter over there. Any of you don't want to go to sleep, just go to our real shelter so that you can spend the night. We get a cooperation from Airbnb. Airbnb give us 8,500 nights to stay for free. For anyone that registered to our system, and then Airbnb would shuffle them to a resident area that they can do and take rest on that night. And about the site that we do, can you move a slide a little? Backward ค่ะ ขอโทษค่ะ backward. Okay, I'm gonna okay, just stop here. To the search and rescue within the site, that was, to me, if you ask me, I divide it into 3 period of time. First, 72 hours, and then first week, and then another 4 week, and then last week. The reason that I separate into this and just this, the first 72 hours, the most difficult because we hope that we still have the high chance of survival underneath the rubbles. And also the rubble itself, according to the engineer though, not me. When we first got to the scene and we tried to get into the space, of course, on the management side, it's really chaotic. And we have to set the system, who's getting to where, and separate the area into 4 different grids, A, B, C, D, of course, and then detailing it so that we can pinpoint the spot. On a particular time, the rubble itself is not stable, and they have to put the sensor and CCTV and then the drone to throw over the rubble so that we can see the movement as well as the search and rescue is getting into. And we have to rely on the engineer all along, because usually search and rescue have an engineer with the team. We have to have them anyway. There would be an engineering background in our search and rescue as well, especially in urban search and rescue, pretty much like high-rise building. However, it's not enough. We have to rely on the sensor, the calculation of the rubbles, whether or not it's stable enough. Each time that we're going to get in, our expert, and I think the engineer association also sent team to be together with us side by side on the first 72 hours that we were together. What piece and what tactic, what alternative that we can get into the rubbles and do a better search and rescue. International team comes in. I learned a lot from international team, especially those people who are also engineering in the other way around. They come with a machine, they come with a calculation, they come with the modeling of the building collapse. It's really good to see that model. And I love them the most. And I think this is what I would like to make a highlight of my speech today. In disaster management, I can't deny structural and non-structural in the engineering definition, but in management, we have structural and non-structural too. And in structural, of course, law, procedure, and those kind of things. Non-structural is culture, communication, and behavior. When the international team comes in, what they did is that they asked me whether or not they can send one of their team to talk with the survival, the injured people, because they want to know at a certain time when the building starts shaking, they want to know that whether or not each of the floor, what kind of work they're doing, how soon they can stop, how they're going to run, and how they're going to move in a shaking building and twisting the structure, because they want to pinpoint all together with their machine. We use a lot of machine though, not only single one. We use the machine from several agencies to try to analyze the spot that we can get through as fast as we can. And they came in on the 48 to 72 hour, the international team. And we continue working with the international team until a week has passed. And we have less chance of having a survival. And we try to get to them a lot quicker because it's already way past the high chance of surviving. We deploy more of the excavator and then the equipment into the engineering side to work on the ground. And I then learned, this is I learned, but not only from this event, I learned it from, we used to have a bridge collapse before last year. And I learned that a person who owned the biggest excavator is private sector. Not a surprise. They build high-rise building every day, not public. Public, we don't build high-rise building on our own. So the equipment was there at the private sector, and also skillful person who can drive efficiently, effectively with the accuracy and speed, private stuff. So they work together side by side with us in terms of this equipment to get in. But it's really difficult because 26.7 height meter in terms of rubbles, we have to have it planned out that we actually going to get into area A and D first, so that we can make it a little flatter and firm so that our excavator can climb up and then work on the channel and then make the gaps in between the B and C, while we are trying to identify and get to the point of B and C where at first we believe that it should be a lot of people there, so that we can get them out in terms of that. When first week passed, during the next 4 weeks, this is an operation that we try to reduce the height of the rubbles So we get the excavator on the flat ground that we make on the area A and D, and trying to get indirectly at the back of B and C, where we believe, because I don't know if I'm going to use the right word, the lift core, the core wall is actually on the back B and C zone, and also the stairwell that using in the fire exit, and that's how the team is trying to get in and work side by side. It's not a very it's the different people been asking me, because they know that I was somehow researching on 9/11 as well. They asked me how different the two cases are. To me, I think because of this building collapse, in our hypothesis that something it's wrong with the building, because none of the building collapsed, only this one. Because of that, the evidence, piece by piece, that we get out from the rubbles have to be very well taken care of. And that also have us to not only, when you have accuracy go together with speed, and then you have to make sure that you're accountable for every pieces of it. It's somehow adding a little bit more complicated process into how we work as well. We balance as well, and we finish the work that even international team think that it's going to take about 2 months at least. We finished it in the search and rescue and the operation of getting the rubbles out until the last stone, 47 days. 47 days, 1.5 months, let's say. So when it's get out, the other difficult thing is body, because this damage is so strong and it's so severe. A lot of body is what's not in a good shape. We're not in a good shape, and it's torn apart. At the last day that we get the last stone out of the area that happened, we identify 98 bodies off of 96 name list that we have as a worker. 89 off of 96. However, on that day, since when we get the last stone out, we also have another 294 pieces of body still not identified. I checked last week, we get to the number of 93 off of 96. So the process will be a little longer because of those shape is somehow the pieces is so too small, and the DNA extraction is getting more difficult and difficult to identify. So when we finish is right now, if you ask me about the investigation, I can't answer that question. As Thanes and as Amon might be able to talk more in terms of structural kind of elements in terms of this building rather than the management. And one thing that I want to mention too, after this operation, is how we help Bangkokian to investigate the buildings that have left in terms of recovery process. Is really still very slow. If I may use this chance to ask for another assistance from the association, it would be really grateful. The reason is that, can you move slide? I'm sorry, one bit to the leave and the other one, ka. Next, another next. Okay, ka. Thank you. We'll stay here. Back. Back one slide, please. Another number four that said financial help อีกแผ่นหนึ่งค่ะไปค่ะ one more stop ค่ะ okay thank you ค่ะ the other thing that we run into that is not quite easy at all is that the engineer might know best. It's the compensation, the reimbursement that we're going to give to people. Right now, as I said, only through Fongdu, 20,000 cases report. But when we open it as a district office to have an official report, 45,633 cases report. With this 45,000, of course, is usually minor and cosmetic damage. Nothing has to worry about a structural damage because the two buildings that structural damage already been retrofitted and fixed. However, by law and by regulations, we have to pay only to the certain damage. Anything that cosmetic, make it a little bit more beautiful, go back to the previous condition. Not by the law that we can do it. It means that one crack, hairline, let's pretend. Let's use one example. Hairline damage. About 1 foot, I guess. 20 centimeter. Only one those crack. Then thinking about the painting that you have to paint this crack to make the crack go away, not color the whole wall though. It's like what, $1. Am I right? So this doesn't speak well in terms of expectation of people who knows that it would be a financial support, even if it's such a small reimbursement or compensation that we help. But yeah, I actually be able to manage by calling all of the engineers that I have and sit them down and said, come here, make a table, each of the damage in which we're going to measure, and then use the regulation of the procurement, how much that we can pay the people. Just make the table out and use it as a standard. I am not going to let the engineer go out there, use their own discretion or use their own consideration in terms of naming how much the damage and the cost it would be. Because if years has passed by, when people come inspect how you paid the people, you're going to end up having a lawsuit or a file. So just get the standard out. And my engineers get the standard out of how we're going to actually calculate the damage and have the financial assistance. So far, we get complained a lot because it's too small of the money. But that is a good point of it is, as well, two sides of the same coin. It's small, but it's from BMA. Guarantee that the damage occur. So you can use this evidence to your insurance and get claim. So it helped in such a way, even though it's a small number. So it's helped a little bit in terms of that, in terms of reimbursement as well. Last but not least, let me conclude this. I'm not gonna bother a person who hold my slide, but if you can find, it would be one page talking about size monitor, and that I'm sorry นะคะ มันจะอยู่ในข้างหน้าไม่เป็นไรค่ะไม่เป็นไรเอาแค่ challenge ก็ได้ค่ะ I'm sorry ค่ะเอาแค่ challenge ก็ได้ค่ะ on that day that I talk about the building, actually it would be only building that I put size monitor on. It's a city hall too. We have 2 city halls in Bangkok. We put it there because our city hall too is 30, the height is equal to 37 floors. 37 floors, and we put the machine ไม่เป็นไรค่ะไม่ต้องแล้วก็ได้ค่ะเอาไว้ที่ตรงนี้เลยก็ได้ค่ะ we put the machine over there, and on that day I have to use my hand instead. I'm sorry นะคะ I just think about this graph. The building, the city hall too, the threshold of the building that it can move is a graph like parabola. I think you are all engineers, you know, x y z, right? When you calculate into a threshold, it's the graph is about my forehead, but our building city hall to only move at my mouth level, so it's really far away. It means that if we have this kind of information forwarding into any communication of my doctors in the hospitals, I have 12 hospitals and I have 8 different high-rise buildings in these 12 hospitals. If I can put this sensor, the size monitor in, it means that there is no need for me to move the critical patient. And it would make it's more kind of like safe, and it's safer for my patient as well. Because as I know, the parameter and the calculation of the resistance to the shaking or the moving ground for the most vulnerable building, pretty much as hospital, it's I don't know how twice as much or 3 times as much as an indicator for the normal building. Then the building is not going to collapse that easy if it's built at the standard and have it checked annually that nothing affect the structural damage. If I have that machine, the most vulnerable group in the hospital would actually be much safer. So I think that's what we try to manage within Bangkok after the lesson that we learned. And as I said before I end, if I can pick one punchline or any highlight, I would have said that I come from disaster management field. I am not a purely engineer, but I have to be able to understand some of the engineering work so that I can connect with the policymaker or the search and rescue and people on ground. I think this event teach me a lot. I learned a lot during this operation, and I realized how much important transdisciplinary is. We've been fond of interdisciplinary and multidisciplinary for quite a while. It's a combination and integration of all of the disciplines together in one place. I agree. But this time I learned that the transdisciplinary, where one disciplinary or more than one might have to comply with another disciplinary, even though it's not 100% answered by our disciplines. I think the transdisciplinary had taught me that not only we need all the discipline to manage it very effectively and efficiently, it also helps us and teach us that we have to allow another disciplinary to take domain. And maybe I have to step back a little in some area. For example, I want to pay reimbursement a little more. My engineer said, Ajahn, when you end your terms and those inspection come in and ask, why are we paid this such amount of money? We can't, even though we feel bad for the people, but the rules and regulations stay, and it has to be at the standard or proficiency of engineer to be able to explain the damage. Otherwise, we cannot quote a quotation of price. Okay, I step back. I think that's what I learned. That's what I learned the most, and I appreciate this and also opportunity for me to speak here. And I already exceeded the time for 4 minutes. I'm sorry. If the times allow, if the host allow, I might be to answer a quick question, one or two, I guess, if you allow. If not, thank you very much for inviting me. Thank you,ค่ะ.
Thank you, Dr. Tavida, for a very insightful information and first-hand experience sharing. And we're truly thankful for your hard work during the early critical hours after the collapse happened. Moving on to the next interesting fact-finding sharing from our speaker, Associate Professor Anek Siripanichkorn, the member of the Board of Council of Engineers, Thailand. Dr. Anek has been appointed to join the fact-finding task force on the collapse of the State Audit Office building. Dr. Anek will be sharing with us today is the unraveling the mystery of building collapse, key lessons for the safer future. Please welcome Dr. Anek.
Thank you, Raskupu. Okay, we begin with my presentation. This topic is unraveling the mystery of building collapse, the key lesson. And be here in the name of member of the board, Council of Engineers Thailand. So my presentation will be covered. The first one will be talking about the earthquake on very soft soil basin, Bangkok and its neighbors. Somehow like we have more than 10 provinces, more than 10 cities that we have the problem of soft soil basin that is affect our building in Bangkok. Right? The second one, I will show you the excitation of 28 March 2025 of State Audit Office of the Kingdom of Thailand, or we call SAO. This building is have the height of 137 meters. The building is somehow like a square. It will footprint 40 by 40 meters, and the earthquake is in Myanmar, very long distance from Myanmar to Bangkok. I think I estimate that about 1,000 kilometers. So we're going to discuss on the engineering investigation on collapse of the SAO building. We have our mandate that we have to report to the government, but within 90 days. So this one this evening we will talk and we will conclude the report that we will send to the government on this coming Monday. And finally, I think I have to mention about our iconic skyscape in Bangkok. We have a lot of skyscape in Bangkok, so I think some of the building has used very nice, very pretty structural system that is very and we can stand for the heavy winds, and this one we prove that only one building that has been collapsed in this event. I think I want to speak about the characteristic of the magnitude of the earthquake. It is about 10 times in each magnitude, but in each magnitude we have see that in the earthquake it has a lot of frequency, but in structural engineer we will take the term of period, right? The period is 1 by frequency, so very much frequency we will come up with a small period, right? So the building that have the natural period very small, maybe will be somehow like a resonance, so it will be damaged for the low-rise building. This is the response spectrum that I have to use this one to explain how we looking about the building that nearby the active fault that almost from the west of the country up to the northern part. This one is the example in Chiang Mai, is very in the north part of Thailand. You can see that the spectral acceleration, we can see that for the one we can see that this one is a very famous formula from Newton, F equal to ma, right? So we check the seismic force divided by W, right? And this is somehow you can see that in the low-rise building as a 2-story or 3-story, they have a maybe will be the resonance of the small period of the seismic. So for 2 and 3-story height, the seismic force may be from this example maybe up to 62% of weight of the building. And if the building is higher, somehow like a 7 or 8 height, maybe this one spectral acceleration will be reduced. This is the one that nearby the active fault, but in Bangkok, you're going to see what happened in the SAO building. So when we're talking about the period, we have to mention the first is the natural period of the building, right? This is the 3 height of building: low-rise, medium-rise, and high-rise building. So for the tall building, or they gave a flexible building. So the time that we call it the period, the time that they come up swaying and going to the original configuration maybe take a very long time, right? So the tall building, they have a natural period is quite long. In this graphic, you can see that for 60-story height, the natural period maybe come up to 7 seconds. But for the shots, we say that very steep, so the period is very small. That is, I said from the previous slide that in the nearby fault, active fault in the north part of Thailand, 2 or 3-story high building, it may be affected by the earthquake. So this one is somehow like a resonance. So if we looking for the small building, 1-story height and maybe 10-story height, the natural period is different. So if you reflect on the peak wave that occurred in the earthquake. And for this one, I said for the previous one is the spectral acceleration in northern part of Thailand, but this one is a response spectrum in Bangkok Basin. You can see that from 1 to 1.8 second, the SA or the spectrum acceleration will be reduced. This is the one that we have in Bangkok. But in this incident in earthquake on 28 March is different from this one. So I will talk about long distance earthquake. We have some report. This is a 3 cities in the world, right? 2 in Mexico and 1 in USA. They have a wave, maybe say that the second wave from the excitation in the epicenter. For the first one in Mexico, right? 1 minute, 900 kilometers from the epicenter. The second one is 1,800 kilometers. So this one, if the wave is coming up and pass the same media, so it may be make any difference. The wave will be decreased. But this one, you can see that the wave is getting up, right? Because this one maybe come from the soft soil. So the reflection of the wave with the different media when the wave comes through under the ground. Right? So we may increase the magnitude, but the period may be not a short period, maybe larger period. Then this one is going to affect our building in Bangkok. And this one is the earthquake report at Mexico City in 1985. The magnitude is 8.1. Epicenter is 300 kilometers from Mexico City. We see the damage report that estimate 10,000 people were killed. Property damage in up to $5 billion. This one is in 1985, and we study a lot. So in Bangkok we prepare the spectrum. Maybe I talk about our regulation, our building regulation and standard. We begin our regulation in 1997. Right? At that time, we have only 10 provinces, 10 cities, starting from Kanchanaburi, the western part of Thailand, up to the northern part of Thailand. We have the new one, the business regulation that is 2007. This one is covered 22 provinces. And at the time, we also have the standard. So we can use a standard to design for the earthquake resistance. And this one is the first one that we use in Thailand, estimated at 2009. And after that, we have a lot of standard and regulation that can permit the existing building to be retrofit or reinforced to resist for the earthquake. And very, very important standard earthquake standing change from 2009 into 2018. Right? This one is I have to say that the concept of this standard may be follow the ACPE 05. This is a very famous standard that you use in around the world. This one in 2018, right? And now we have the new military regulation that is in 2021, effective from 4 March 2021. So the question is that SAO building is what time that they have begin for the design, because before the construction they have to submit the design in which regulation or in which standard that is used in their design. So I think I have to say about the spectrum acceleration, right, that we use in Bangkok and in the Bangkok and the neighborhood, Samut Sakhon, Samut Prakan. Now we extend to Ayutthaya, Nakhon Nayok, very large basin, right? When we call the Bangkok Basin. We use the ACE 0.505, the one that we expect that we have the maximum considered earthquake, that is in 2018, right? So our standard will not use this one. This is very high and the maximum considered earthquake. So we have to reduce to be a design basis earthquake that we have to regulate it, to standard. The first one is 2009, it's lower than the new one is 2018. Right? And the last two curves, this is the peak wavelength spectral amplitude that we detect from the seismic station. We check in Bangkok. We have nine stations, and you can see that most of the time we have a lot of peak length. But in this one, I will show you another accurate. This is a complete 7-day from the incident. This is the one that we have to use in the investigation. This peak wavelength spectrum amplitude on 28 March 2025. So we have to compare two standards. The first one is 2009, the other one is 2018, because this project has been designed for that maybe some say that 10 years ago. So we have to check that what the one that he take the approval from the authority. So we use the design basic RDBA in 2 years. You can see the lower one, we have a lot of wave, right? And this one is very interesting. And this one is maybe is different from our understanding, because our understanding is, you can say that from 1 second of period to it will be reduced, right? You can see that the 2 dBA is reduced after 2 seconds of period, right? But in this time at 28 March 2007, in this year, we have a lot of wavelength that we have many peak, right? You can see that in our standard, we use the damping 2.5% and 5%, right? But in this one, we have to say that this building is not an incomplete building. Somehow they use the cladding, they maybe installation of the wall, maybe not. It's not complete. So we have to check for the 1% damping. You can see the 1% damping is very high. Maybe some period is greater than the standard of our building law, right? And you can see that they have a lot of wavelength in a long period. Right? We can see that it's very different from the spectrum that we provide in our new standard in 2018, right? Especially for a long period, 4, 5, 6, 7, between 6 to 7, maybe affect to the 60-story height in Bangkok. Right? So we have the problem with long period excitation is very interesting. So after the investigation, when we submit the report, we will make a further study to improve our standard. That is quite same as many countries, because the situation of excitation is very difficult and very complicated. This one we accept that our spectrum acceleration that we provide in the standard may be not enough for the long period excitation. So this one we can see that the shape of the building is from the low rise to the medium and to the high rise building. So this one, I think this is very key issue that we talk about in the social. We can see that I show the plan of the SAO building. Right? This one we have the structural system like we have the core wall interface with the frame, right? and the floor is making by 4-tension flat slab. You can see that this one, if you're looking for the center of rigidity, that means that when we find the center of the strip net, of the strip of the building, mostly depend on the core wall compared to the center of band that maybe we call the center of mass. This is the center of this band. So maybe this one, if not coincide, we will have faced with the splitting effect. There is torsional effect. Somehow like this example that we can see that different wall in this span, right? In the western we have a larger wall compared to the east, and the north is larger than into the south. So this one you can see that the center of rigidity and the center of band is not coincide, right? So we will face with the torsion effect. This one is we call in the standard that this is a irregularity system. So the designer have to choose the alternative method. They cannot use the static one. Maybe they can have to use the dynamic response. For this one, if the building complete, we have to set up the CMSCR to coincide in the middle of the building, right? This is the one that we're talking about. So when the government set up to make a investigating committee, so we have to make a dialogue. The first one we talk about the construction process. We have one committee that they check the relevant information somehow like a RFI request for information or request for material that we use already in our construction the industry. We have to check the daily request, daily report, and the report of the testing of the material. We check in the variation order and the approval of the contract changing. The major changing in our project is that the owner and all the parties somehow like a consult engineer, designer, and the construction company. They change the major one is they change the thickness of the wall from 30 centimeters into 25 centimeters that will affect to the strength of the core wall. So this one we have to determine the competitive the rate load, that because this one the building is not complete, so the vibration we concern, so we reduce the damping from 5 to 2.5% and 1% to check it up that what happened to the building. The second one is the material used in the construction. In this project is made of reinforced concrete, so where only two major material that is concrete. In this project, they use a very strength, somehow like a core wall. They set up the strength of concrete to 50 megapascal, right? And for the upper structure and in slab, they use the strength is 35 megapascal. And the reinforcing bar we have to see. We have a lot very size and very class. And the one that we use in our common practical in Thailand, we use the copper to make the spice for the steel bar. So this committee we going to on-site sampling and test, right? Somehow like a concrete, we have to check it with somehow like a P-test for concrete. Like you use ultrasonic pulse velocity to check it up that the sample that we retrieve from the site is okay or not, right? So UPV that have the Weerasiri more than 3,500 meter per sec will be going to have the test. This is the one that we very concerned about, because as we can determine that when we got the poor sample, because the sample have been affected by the total collapse of the buildings. We check the density to check the porosity in concrete. As bar, we use only the one that embedded in concrete. And very important is we going to make sure that the design of this building is okay or not. Right? We divided into 2 groups. We have 6 universities in Thailand that challenge to have the study on this one. We divided 3 universities to run for the construction contract drawing. This one uses the elastic and response spectrum analysis, or RSA. Does it mean that it's come up with the standard in the year 2009? And the another 3 universities, this one will be going to have concern with the as construction drawing. Right? Somehow, like the thickness of the core wall is reduced from 30 to 25. Not complete of the wall and the cladding of the buildings. So this one will be checked on the nonlinear and modified response spectrum. That is the standard into 2018. So we run our investigation by this dialogue. So if I want to conclude that our flowchart for evaluation and investigation of SAO building is come up with one is 3 university run for linear elastic model, and the other 3 is done non-linear elastic model. So we have to check the model analysis, and we have to compare. For non-linear is very complicated, right? I told you that the practical or the professional structural engineer in Thailand, they use any non-linear elastic because it's very complicated, right? And now we have to check that what happened to the building. So we're going to run through the non-linear static and push over analysis. That I will tell you the detail after that. The model analysis we will analyze on the model under the railroad to find the natural period in the building, right? And for nonlinear the dynamic analysis, we use the time history, and when we check with the PWSA station, then I showed you that this one will have the real one, the PWSA real one in the date of incident. And after that, we have to compare the analysis and the result of the SAO building. And now I said that we have finished our investigation already. For the nonlinear, we have to maybe this is a very general step that involved in a nonlinear analysis of the building, right? Somehow like a project definition and data collection. We have the building geometry from the construction drawing and as-built drawing that we get informed the office of the construction. We have the material property, right? But in somehow like a nonlinear, we have to check the material property because it not behave in the elastic behavior. Maybe we looking after the elastic, so we have to check in the model. And we use the specify to PWSA in the real one. This is the element and section and the material model. We use the two researchers very famous, very famous. That is a man there for the concrete construction and Pinto in the steel reinforcement. This is the one that not the elastic one. Because I think the true the true result when we come up with the nonlinear analysis. The structural model, we use we have 6 universities, so they use they use their own program, right? Sometimes like ETAP, SAP, bus, Sismosat. This is the one that we let them use their own because we have to check it. And the element modeling, we often we will modeling the beam and the column that I show you after this slide, that somehow like equivalent because we use the fiber method to check the shear wall. This one is very important because we can see that the collapse somehow like a pancake from like a vertical collapse. It may be caused by the shear wall collapse. The mass and stiffness distribution is very, very important because we have a lot of mode shape, right? And so we have to check that what is the mode that influence the behavior of the model of this building. So the mass interpretation will be checking up to show that what is the most important mode shape, right? Damping, I say that 1% damping is also considered, right? And the loading is we have to use the gravity load, right? Somehow this one is is given by law and by the standard of our building standard in Thailand. So the seismic we use the real one at 28 March. This is a building model. This is I have received the information from Professor Sutat. He is the leader of the University of Technology Thonburi team, right? And they use this is the parameter of the material that used. You can see that the FC prime is 420 and 575 because the one is greater than the specified. Expected that may be higher than the nominal strength that they use, and the lower one is we can retrieve from the test from the site inspection, and the FY is 5,000 and F5080, and we use a Young modulus because we have to check it up the behavior of the gun. It should be known that at the 419 they changed the core wall to the column because they let to have more space from 419 to the top of the building. Right? This is a discontinuity, and when we model, so we have to model somehow like an equivalent beam. Right? We check it out like a rigid diaphragm for the frame and the diaphragm is a horizontal subsystem, right? And the one that is, you can see that it is a lot of core in this building, right? This is we check the eigenvalue analysis, right? Mode, first mode, second mode, and the third mode, right? The first mode is sway and twist. The second mode is only sway, and the third mode is twist only, right? So this one has been checked from the eigenvalue analysis, right? And we compare from the pushover and the mode shape from the eigenvalue. This one is compare, and we confirm that the major mode of this one is what is the major mode of that influence the behavior of the building. So this one you can see that in the left table, this is a first mode, second mode, and third mode, 5, 6, right? And another in the middle table is somehow like a effective model mass percentage. You can see that the model mass percentage is very much in the mode 1. So this one is the way that we consider very carefully in the mode shape for the first mode shape, right? And this is we can ensure this result to show that what happened to this building. So this is a mass participant factor that we use in that one. And this is the one that I call that the first mode is sway, right, and twist. The second one is sway only, and the third one is twisting under the torsion. We have to make the model calibration with recent research. And I said that their test, they have a lot of in laboratory tests, right? And this one we check our model with the test result. We use the reinforcement of this one that they use in experimentation in the lab, and the one that we use in model, and the result is compiled. Right? This is one where we have to check it. And also the strain that occur in what to say, in both concrete and reinforcement, we have to check it out. This is a model calibration also, right? So after that, after we model or we calibrate our model, so we're going to run for the result. The one that we can see that you can see from the figure of the building, the 3 columns. Maybe this diagram is from the first floor to 4th floor. So this one is 3 height of the column is very cylinder. So it should be make our investigation what happened first, right? Somehow say that this cylinder column is maybe buckled before the collapse, the total collapse of the building. So we have to check with the recent research that we have to check the strain, right, of the reinforcement that we use the result from our model. The performance, we will check the displacement, right, and we check the plastic hinge formation, and the very important one is we check the demand per capacity ratio that not be greater than 1, right? And the Bayesian worsening moment we check on every parameter to ensure that our model is suitable to investigate. And this is a comparison of the performance objective. Right? So we put the nonlinear adaptive pushover analysis, right? From the north to north-south and north-south and east-west in the vertical and in the horizontal, respectively. Right? The model is we use the load, right? And we target the maximum target displacement at 1 meter on the top of the building. We check the strain, we check the force. Every type of force somehow like a bending, right? Where bending will be induce a vertical compression and tension in the core wall, and we checking for the shear. But very I think you know that very difficult because maybe on the program somehow like an ETAP, maybe the model is unable to simulate shear deformation, right? They're looking for bending. Maybe bending is a measure for that computer model. So for the shear failure, we have to simulate, right? Somehow like if the fractal stress is maybe strength loss. After that, we will check for the shear capacity. That is very difficult. This is a preliminary result from nonlinear response history analysis, right? We can see that from the PWSA, we got the loop displacement approximately 23 meters, right? And this one we get into our calculation after that. This is the pushover result in east-west direction. We have seen some defect that occur in maybe in each core wall. We have a lot of core wall, and after that we going to push it somehow, like you can see from the graph that we looking for the yield, right? The wall yield or the beam shear or the wall clash or the yielding of the reinforcement. So we put this one. The target is 1 meter. And this show your wall shear DC ratio, DCR, right? 73 centimeter displacement in SN south and north direction, and lateral of the plan of the building, right? So we can detect some DCR that greater than 1, approximately by maybe at the floor, the 3, the floor number 3 or 4 somehow. Then we can check for we can find the DCR that greater than 1, and we also check with the strain, right? The strain it will occur, especially in concrete. The strain, the magic number is 0.003, right? Greater than that, we will find the crushing of the concrete. So the wall strain and the strain in our building, especially in core, we have to check it. And this is from 33 from the landing of PWSA. So we try to push more than that at 34 centimeters loop displacement. So you can see that we have a lot of DCR that greater than 1, and this one can see that what the thicker point, what the thicker floor that beginning for the total collapse. We also check the strain in the reinforcing bar, right? Somehow some strain is greater than yield strain, and this one we also check at the ground to the second floor. This is a result that we get from the investigative field. So the magic number, you can see that the strain minimum is 0.008, right? Then this is maybe for the FC pan about 30 megapascal, right? So this one is the one that we have to look after that, because we expect that the failure is coming from the crushing of the concrete in the wall, and we will make the review for many research to see what is the basement concrete crushing or not, right? But we found in our investigation that it's not come from the footing or the piling of the building. And this one is the one that we use and explain how the difference of the strain that we looking for, right? And this is a ratio of shear force to shear strength of the RC wall. You can see that there are a lot of DCR that greater than permissible in the code. And we found that the crack pattern, I think the crack pattern will be shear failure that is different from the crack pattern of the somehow like a diagonal tension, or that is called induce tension and compression, right? Becoming like a shear failure. However, when we looking for the forensic engineering, we have to look for the evidence that occur in that day. We have the data, the prelim data from the video casting, right? We have 10 clips from different sources. So this one is very important, because we have to check that whether from the 10 clips we have to make that what is the thicker and where is the ticker occur in our collapse line. So the video clip will be manual synchronized by visual cue, right? And the result will show the incident timeline. And this one is, you can see that we have 10 clips, right? We rename to 001 to 010, right? The frame rate is 30, right? 30 frame per second. So our investigating committee is looking very carefully in each second. We have 30 frame, right? Very small, because this is very important. And the frame, we can see that we have 10, right? We have 10 allow the building. This is come from the people that take the video record by himself, right? We have 10. Right? So our duty have to synchronize this one with the same, right? With the same time. So the first we will be checking up the camera number 1 to another one, and we can check everything. The checking is something like we see the video, right? Maybe in at that time, maybe something falling from the upper floor, right? Something like somehow like a cladding or the preventing plastic that cover the building, maybe change the shape or reform, something like that. So we can make the synchronize from this one. So the first one is synchronize 1, 2, and 3, right? Because the file, the name, the time that they're taking the video is somehow like very closely, and after that we make the synchronize already 10 clips, right? So we can have somehow like only one camera, right? And can take all of the building. And this is we come up with the incident timeline, right? What the figure that you see that 2080 is a frame number, right? And we can see that what happened along the incident time. So this one, I think the ticker is in 4th floor, right? And we check the shear failure at the 4th floor is the same, right? Somehow like when the failure occur at that floor, at that core wall, so we cannot push over anymore, right? Maybe it's end up with 40 loop displacement, and we have a lot of consequent failure that occurred in this one. So this is the story that we taken during our investigation. In the last my presentation, I think I have to show you our iconic building in Bangkok, right? This is the outrigger and belt truss system, right? This one is maybe very suitable for the center core, somehow like a large center core, and we have to reduce the reduce the size way of the building, especially in the wind action, right? So the way to reduce the size way of the building is we put a cap truss or the ticker members and fix and assembly with the auxiliary columns. Somehow, if you have the wheel load from the left, so the auxiliary columns will be make a couple that induce compression and tension. So this couple will be reduced, will be begging to reduce the size way of the building. And this is the behavior of the outrigger belt truss. So this one is our building. We have 2 buildings in Bangkok, and the outrigger should have to communicate with the belt truss to ensure that all the exterior column or the perimeter column is acting like the one that we take from the central core. And this is show the structural system of outriggers and bell truss. In Bangkok, we have a modern tower, right? We call Mahanakhon Tower. Is approximately 320 meter height. Service in 2016, right? This building is 77-story height. They have a large all wall, so behavior like somehow like a bending mode, and they have a there are no any columns within the core wall and the perimeter column, so they try to use this one like a outrigger and bell truss. Right? But however, this one is made from reinforced concrete, so the thicker is somehow like a very deep, very much beam, very much capacity of the beam, last beam, right? Last step. So this one somehow like a thicker RC thicker, right? And they use the RC wall to be a bell truss. This one is serviced in 2016. And we also have the outrigger one in 1999. It 58.4, 270 meter height. This is office in Bangkok in Surawong. This one we call the Empire Tower. We have 3 tower, right? A, B, and C. They use the outrigger and bell truss. This is the one that we have in Thailand. The last one that I show you is using the structural system of tube structure. This is how to make a structure to give the largest moment of inertia. So they form the structure form with the closely spaced column and connected with the deep spandrel beam. So this one is somehow like a making a tube structure. We have known that Empire State in 1931 is very famous, maybe the most famous tall building in the world. Right? They use the frame and wall somehow like a shear wall, when like a frame, right? Like a column, slab, and core wall. But when we have one building very famous also is the John Hancock building in Chicago, that maybe the service at approximately 1976, maybe like that. Right? They use the tube also, but the spacing of column is not closely. They use a wide spacing of column, so they have to put the truss tube. Right? This one show that the structural system of the building can reduce the price of the building compared to Empire State. They use maybe only 55 or 60% of the steel that used in John Hancock. We have the one like this in Bangkok. We call this one like a Bayok tool. Right? Once maybe the highest building at that time, serviced in 1987, 304 meters. You can see from the section of this tower, you can look for the diagonal truss tube, right? So make this one maybe inner tube and truss tube. So this one is very strong, and this is the answer that why our ancient building, our tall building can be very strong compared to the previous seismic in this time. Right? Maybe I come to my presentation, and I have to say that thank you for your all kind attention.
Thank you, Dr. Anek, for a remarkable presentation. We have a couple of questions from the audience. Do you still have some time with us?
Yes, sure.
Okay. So the question is that, do the structural designer provide bottom rebar to prevent progressive collapse as per ACI 318 8.7.5.6?
Maybe this question is belonging to the the gravity.
The analyst discussion.
Somehow I think this one is the seal that prevent the preventive collapse may be using for the design of the slab, right? In our standard we have also, right? But this one is not the gravity load, it's a lateral load. So this one is we concern about the one that occur, that the force induced in the element. But in this building they use post tension flat slab, right? It's a pre-stage, so they have to use the steel to prevent the gravity collapse, not the lateral collapse, right?
Okay, thank you. And so the later question, I'm not sure if you will be able to answer this, is about remote IoT sensing of the seismic data at regional levels to build digital twin of AI earthquake prediction system would be powerful real-time tool for the ASEAN region, especially in the vicinity of the tectonic faults. To what extent has remote sensing been deployed within the ASEAN region?
Oh, I think this question is very important, but now we may be not going to that point.
Okay.
We try to make our information for the building. We have trying to mount the ambient vibration, right? Somehow like we want to know the natural period of our building to not to meet the response for the site, the earthquake, right? The first one we just only put somehow like what we want to know the vibration of our building, somehow like a natural period of the building. But this question or this comment is very important for our building in our region. We try to make what to say to make the working team, right, with our neighbor, our friend, right, in ASEAN and on behalf of Council of Engineering Thailand, we accept this comment, right, and we will working together in the future.
Yes, thank you. That maybe is a good question for a panel discussion later on. So last question. Why the stair elements is not assigned non-linearity? I'm not sure that make any sense.
Because what to say is somehow like a large opening, right? And what to say, the stair is between 4 and 4, right? So this is we have to make the what to say to make the model of the wall somehow like a one or two unity bed, somehow like a panel, but the other one is somehow made the shell model, so it's very difficult in what is it in the stack hall, right?
Okay, so that will be all for today, and thank you very much for sharing the presentation with us today. And next session will focus more on the standard sharing and discussion, aiming to improve the engineering standard in ASEAN. We have experts and practitioners from various countries with us today. Allow me to introduce them before we begin the discussion session. Our first panelist is Professor Wayan Sengara from Geotechnical Engineering Institute of Technology, Bandung, the Institute of Engineers, Indonesia. And our second speaker is also from the same institute, Professor Engineer Iswandi Imran, Structural Engineering Research Group. And our third panelist is from Myanmar, Dr. Somin, who is an RFPE in Thailand. He's from Consultant and Supervision Strong Force One, the company that he's working in Thailand. And our last expert is from Thailand, Mr. Niwat Thanpitinan. Mr. Niwat has been assigned to be a member of a special committee under the House of Representatives to enhancement of construction and safety standard, indemnification for damage and systematic progression of construction and contractor industry, who is also very kind, agreed to be the moderator for the session today. Kun Niwat is also the monitoring committee from Council of Engineers Thailand as well. And so I will leave the stage to the gentleman for the discussion. So please welcome our gentleman.
Good afternoon, everyone. Welcome to the Thailand EC ACPE Forum once again. In fact, we have organized this event a few months ago, and it was really successful. And that's why today, I think it's the right time we should organize this forum again to discuss a very important and really focused by the engineering professional around the region. Okay, and that's why the Council of Engineers Thailand have the opportunity to invite so many experts from all of you who have listened from the beginning. You may have listened the very insightful information from our Bangkok Deputy Governor, and also the expert like Dr. Anek, who just gave us the lecture and very informative knowledge about the earthquake and all the design matters related to this incident. But anyway, I'm sure that many of you are also looking forward to this session, which is a panel discussion among another 3 experts, okay, which our moderator have introduced already. So I don't want to spend time to repeat it again. But 2 of them will be joining us online. Dr. Sengara and Professor Imran from Indonesia. But luckily, I have one more speaker sitting beside me, Dr. Somian from Myanmar, so I don't feel that alone. Okay, so but anyway, since we are running out a bit late from the agenda, I will try to make our panel discussion pretty brief but productive, of course. So in brief, I will go in order like this. I may ask our speaker from Indonesia, Dr. Sengara, to be the first person to share some information by his slide. And then we will continue with a couple of questions if we may have, okay? And then the next person may be Dr. Somian. And then Dr. Imran will be the last person in the similar pattern. They can show their slide, but I already insist of them, or the distinguished speaker, not to lecture too much, because we want to make this session really more discussion pattern and also more interactive. So all the audience today, please feel free to send us the question you may have right now through the chat box, or prepare to answer by yourself if possible later. Okay. So in this case, I think I would like to invite Dr. Sengara to start his presentation and sharing his knowledge with us.
Good afternoon, everybody. Thank you very much for the invitation. I would like to share our experience on the Indonesian earthquake disaster reduction efforts for the last maybe 10 years, 15 years. So can you see my screen, and can you hear my voice clearly?
Yes. Yes.
Okay, thank you. So let me just highlight on the earthquake disaster in Indonesia and what is our framework for disaster risk reduction in Indonesia, and let's say within the ASEAN or within the Asia. I just would like to talk about two main topics here with some of the details, not too details because the time limitation. The first one is the seismic hazard and risk targeted ground motion mapping, which is one of the very important aspect in the earthquake disaster risk reduction. This will include some of our effort in revising the hazard maps to up to date in 2024. We have the 2017 hazard map that was actually adapted up to recently, up to date. And new what we call a risk targeted ground motion that we refer to the international building codes and also compliance and enforcement of building code process in Indonesia, and how we put our effort on the engineers capacity building. But there going to be another effort for resilience community, like for disaster building assessment survey and damage modeling, and an earthquake recognition survey and report after earthquake. And the last one will be the school safety and retrofitting. Well, in Asia, actually, we are on the similar or the same tectonic setting that most of our Asian countries is subject to the, this subduction source that all of our Asian countries, particularly Indonesia, Thailand, Myanmar, and some other part is affected by this seismic source. As you can see here, I don't want to scare you. Indonesia has experienced many earthquake disasters for the last 30 years, and many of the one that I highlight in orange, that is the large one with a magnitude of higher than 8. It also has a collateral tsunami, and the last one we have Palu earthquake in 2018 that caused liquefaction. Maybe there's the largest liquefaction occurrence for in this century. And also we, of course, in 2005 we have a very large 9.2 earthquake. This is typical damage or collapse of many power building in Indonesia. Even though some of the building is still intact under the earthquake, but many of our building has experienced various damage level. Well, what is our framework for this, actually, the disaster risk reduction for the future? I think we have a national vision for disaster risk reduction 2025 that identifies some of the perceived item, let's say like build capacity, and also the regulatory arrangement and preparedness strategies that we need to implement for the next in the future. And also we need to enhance the disaster management and emergency response due to this hazard. Well, the Indonesia state of progress in earthquake disaster risk reduction includes one is the master plan for disaster management from 2020 to 2045. This is our presidential decree 2020, and this is managed by our emergency response agency. And then the second one is the 2017 and 2024 update on Indonesian earthquake source and hazard maps. And also in 2019, we have our new revision of Indonesian seismic resistant of structure code for building and non-building as an update of the 2012. So this is actually a process that we have a lot of earthquake in 2005 of the Aceh earthquake that we have a commitment to revise or update our seismic hazard map and and also building codes. And one of the response to this many earthquake disaster in Indonesia is the seismic hazard and risk targeted ground motion. We would like to have to update our code according to follow or refer to the international building codes, so particularly on the ASCE, American Society of Civil Engineer. For this one, we refer to ASCE 7 2016. That we come up with the 2019 risk targeted ground motion map that as an important input to the building codes, and also the compliant enforcement of the building code process and the capacity. And I would like to share this as our framework. So the one that highlight with red, this is something that related to we are as an engineer, as a professional engineer, need to be aware that the seismic building code and the dissemination and training of the building code, building design, building code compliant for the permit and the construction supervision is a key element to reduce earthquake disaster. And what we do is actually to make sure that the magnitude and the fault, the source is identified as far as possible. So we need the identification of the fault, and also we need to estimate what is the ground motion that we put in our building code, and this is our hazard map that is
Can you have any
specified.
question to other speaker? Feel free to ask.
Okay, yeah, feel free to have a question if you have. So we have need to specify what is the let's say the PGA, what is this spectral acceleration at the base rock, and then we have a site classification to be properly classified, and then so that our spectra for each specific site is identified properly. So this is the process. This is the evolution of our seismic building codes from 1978, and then 1992, and then also to 2017. So this is from 1978 to 2017. We have a relatively significant update on this. And this is the update of Indonesian hazard map, and actually in 2024 we also have the new map which is not currently included or not actually input into the new building code, but we have the hazard map already. And this hazard map is not only for building but also for brick structure and also dam structure. So the development of the Indonesian seismic building code is actually referring to the so in 2002 we have a UBC, and then 2020 at 12 we use ICE 710, and then finally for the 2019 we refer to the ICE 716 standard, which actually become the international building codes. In addition to this, actually we release a new Indonesian seismic building codes, and also the requirement on the earthquake ground motion selection and modification for building. So just now we heard Professor Anek present how we do a nonlinear response history analysis for important building of a high-rise building, and this is also in practice currently in Indonesia. I think later on Professor Iswandi, so Imran will go into more detail on this, but the ground motion and the guideline for that is already available and now is adopted for practice in Indonesia. How about the compliance and enforcement of building? We have an advisory committee establishment and review process currently modified as a professional engineering expert to review the design. And this is by the decree of the local government to have the building permit properly evaluated. And this is somehow so just highlight on how the professional engineer need to have certificate and well, actually need to have license to design, and the advisory team or the expert need to evaluate for the permit. The engineering capacity building. So we urge many of our engineers to update their knowledge through, let's say, the World Conference on Earthquake Engineering, which is conducted hosted by International Association for Earthquake Engineers, to attend the conference every 4 years. So many of our engineers from Indonesia also attended this conference. Local association, Indonesian Earthquake Engineer Association, also regularly conduct international conference on earthquake engineering and disaster mitigation every 3 years, 4 years. So next year we will plan to have our conference in Jakarta, and we invite all of the ASEAN countries also to participate. The international joint workshop also conducted almost regularly, but not too often. From 2017, we have advanced technology for seismic protection, and then structural design of high-rise building with passive control. In 2019, we have a workshop on geotechnical and structural engineering with collaboration with NCRE Taiwan. Okay, that is the first part, and how we share our activities or our effort in Indonesia. And the other effort, maybe I will just go briefly on this because of the time limitation. In 2009, we have a large earthquake also in West Sumatra that caused many casualties and also many building collapse and building damages. And somehow we managed to conduct post earthquake building assessment survey and damage modeling, and finally we have the report to be published on this. So let me start with the post earthquake building assessment survey and damage modeling. We have reference of ATC 20 procedure to conduct this post earthquake safety evaluation for building, which is actually rapid. We call it a rapid evaluation or triaging to tag the building to be red, yellow, or green. So we need a safety evaluation procedure, which is rapid, detailed evaluation, and the engineering evaluation shall be conducted for essential facilities, including hospital and actually many of building or housing as well. Well, the inspector need to be qualified, so we need to have a training for this qualified technical person. I think in many other ASEAN countries also we need this, and so before earthquake we need to have the person trained to do the evaluation, because they're going to be thousand of, like in the case of Indonesia, we have thousand of houses or building to be evaluated, and so we need to have a qualified technical person for this. So in this we have this experience. Many of the post earthquake we tag red, yellow, and green here. So during the 2009 West Sumatra earthquake, we have a more systematic post-earthquake survey in more detail compared to the rapid building assessment. So total of 3,000, almost 4,000 buildings were surveyed in this area. So it will comprise many building construction, building types, medical facilities, educational building, commercial, and also residential structure with various types and construction. And also the survey work entailed 1,700 interviews with residents, and the building of all ages category were damaged, and nominally engineered structure also suffered significant damage. Well, the observation revealed that poor structural configuration, poor detailing of reinforcement, and and the use of low quality construction material is to be some of the contributors to this damage. We involved about 70 engineers and researchers conducted by collaborative effort many agencies and universities. And this is we come up with 9 benchmark curves. This is a damage curve. We call it damage curve or vulnerability curve, correlating the MMI to damage index that we developed from that almost 4,000 buildings damage that varies from slight damage, moderate, extensive to complex. So this is our preliminary development of building vulnerability. Maybe I think Professor Imran will also go into more detail on this if you can, because I'm not structural specialist. I'm rather geotechnical. And then this is the report that we have published through that post-earthquake disaster survey, and some of the papers also related to the findings, including the Sumatra and also the Palu here by the Pushgan and also ITB, and we have PD Jaya earthquake with collaboration with Bilcheng, our local association, and also with ARI United States. And school safety, this is my last thing to share, is the school safety for the include training and also the training for masons. So our school need to be protected so to make sure that our children, our future generation, safe under earthquake in the future. So we have this to be conducted in several provinces in Indonesia, even though this activity is not too aggressive. So we would like, I think we engineer also have a commitment to, even though this is a just a simple building, but many of the building in Indonesia, most of the building damage or building collapse in Indonesia experienced during many of the earthquake was dedicated to this non-engineered building. And this is an example of how we retrofit the building, the school building. This is a recent collaboration with ANCRI and also with our university and also with our local association. This is the school that is retrofitted because we consider the original, the existing building has a high vulnerability to have a damage. So let me conclude to summarize some of the highlights that I have presented and to be shared with the ASEAN countries. The seismic hazard map and also building and infrastructure code for Indonesia has evolved and revised over the last 3 decades. Recent seismic spectral design load requirement for building and infrastructure actually is Indonesia in general directed toward in line with many international building codes. So maybe I think in ASEAN countries we can share knowledge on how our code has evolved, and maybe we can learn each other to have a better building codes in the future. Well, we identified that there's an increase in spectral design loads requirement. This will tend to expose many existing building and infrastructure to be at a higher level of vulnerability and risk. So meanwhile, we have our hazard map revised, and we identify more and more building under higher risk and for the future earthquake. So this preliminary vulnerability building damage model is just one step to have that we can use for the risk assessment process in the future. So now we identify the risk of the building damage, and this is good for for the disaster management agency, and also important for the insurance for identify the risk. So it has been highlighted that earthquake-resistant design and construction of building and infrastructure in Indonesia need to become a priority, and this is a crucial factor for earthquake DRR. So the professional engineers play significant roles in this DRR. So it is essential also to prevent and minimize building and infrastructure collapse or damage from future earthquake. Through all of this, I think I already mentioned that provision of full engineering design parameters, or even though this afternoon we also heard from the deputy governor that we are engineering to have a lot of roles in this, and we need to put proper design parameter for our buildings. So the improvement of building hazard and building code. So we need to also legally put this building codes in the local regulation. Proper design, good quality construction, and also the design enforcement for the building permit, systematic and good construction supervision, and then after that also need I think the disaster management agency need to have disaster risk assessment for the building and infrastructure. So this demand development of continuous enhancement of building and infrastructure vulnerability model. Retrofit of school, essential and vulnerable building. I think we learned a lot from Taiwan. So most of the school building in Taiwan has been retrofitted. So in Indonesia, we have a lot of concern on this the school buildings. And the last is the promotion on enforcement of seismic building code training on and community-based earthquake-resistant construction for building are vital to vulnerability and disaster risk reduction. I would like to acknowledge Professor Isham, Diahkusumastuti, Erwin Lim, and Dr. Udre to also contribute to this presentation and this sharing experience. Thank you very much. I cannot hear you, Dr. Niwat. Maybe you still mute, maybe.
Hello. Yeah. Can you hear me now?
Okay. Yes.
Okay.
Yes.
All right. Yeah. I'm just curious. Since coming August, I'm traveling. I have a plan to travel to Indonesia, to Mount Bromo for trekking with some friends.
Mount Bromo.
So, yeah. Just curious whether that part of Indonesia is vulnerable to earthquake also.
Oh, yes. If you can see from the map, we have almost every week we have earthquake from small 4 magnitude to higher magnitude. So particularly in Java, we all have vulnerable or relatively high hazard. So let's say medium to high. I should say medium to high for the whole Indonesia. So we are expecting big ground acceleration, let's say for the 2,400 years return period between 0.2 to 0.3 on the northern part of Java, and also on 0.3 to 0.4 G for the southern part of Java. So Bromo is also, vulnerable.
Anyway, yeah, so look forward to that trip. We'll see whether and my friend will be able to enjoy our time nicely over there. Okay. It would be
Not
quite
many
challenging.
building though. Yeah, not many building in Bromo though.
Right. Okay. One more question. How does the media in your country mention about the recent building collapse in Bangkok? I'm curious to know about it.
Oh yeah, the media in Indonesia is relatively sensitive. Very no occurrence in the world currently. just directly a minute after that, we already have the news, and many of us are really concerned because I think what in the news is relatively the worst case, the building collapse of the high-rise building. So we so all in Indonesia also really concerned with that, because in Indonesia, in Jakarta particularly, we have a similar high-rise building to Bangkok. So the media response this quick disaster in Myanmar and Thailand really seriously. Even though after that, after several days, diminished, but as many of other countries are saying also. But we are engineer in Indonesia has a big big concern, and would like to to have what is shared for this disaster.
Okay. Right. Next, I would like to give the opportunity to my colleagues here today. Yeah, Dr. Somien. He will be the next speaker, of course, but he might have some questions to Dr. Sengara as well that you can share with the audience, in case you have. Okay. If not yet, maybe later, Dr. Sengara, we will discuss more about the incident a bit later. So next, I would like to invite Dr. Somien from Myanmar, of course, but he is working in Thailand for a long time. Okay, so he also understands the situation in Thailand quite well. So this is also the good opportunity to share his opinion to the audience from overseas as well. Yeah, please, Dr. Somien.
Thank you very much, Niwat, to give me the opportunity. Good afternoon, everyone. So I am Dr. Somien from Myanmar. So today I would like to present my topic as importance of earthquake-related detailing in construction, what we got from the experience from monthly earthquake in Myanmar. Next slide, please.
You can tell. Okay.
Okay. So on 28 March 2025, around 12:50 local time, there was a earthquake, 7.7 magnitude. Epicenter is close to Mandalay, our second largest city. So before that, we have another very severe earthquake, one in 1912, one in 1930, Pago earthquake. Pago earthquake is coming from the Sakine Fault, you see. So on that time also very severe, around 7.2 to 7.9 magnitude. So once in May, once in December again coming. December is near the Pago Phu region, Phu earthquake. So on that time also very severe, we have to suffer. Now on recent 7.7 magnitude, it's also extend to Thailand at the west to Dhaka, China, and up to Ho Chi Minh City. Very, very serious earthquake happened. So when we study the Myanmar, so this is the last time near the monthly 7.7 earthquake. It's called Dhaka, it's called Yunnan, it's called Thailand, Bangkok, and Ho Chi Minh City afterward. So when we look at the Myanmar, we have two major earthquake sources. One is, as you know, Sakine Fault. This is running along the Myanmar center of the Myanmar. So another one is the Sanda Mega Thrust. This is along the west coast. So this also very severe. So when happened, it's around 7.7, 7.8, something like that. So Myanmar have the two very serious source of earthquake. So when we talk about the earthquake, we have two criteria to define the earthquake. One is the MMI. This MMI is the 1 to 10. So from 1 to 5 is the weak to moderate, and 5 and 6 is the strong, very strong, severe, and 9, 10 is the extreme case. So when we talk about the Richter scale, there is the correlation between MMI scale and Richter scale. As you see, 1 to 5 become 3.5, 5, 6 is the 4.5 Richter scale, 8 to 9 is the 6, 9 is the 7. So last time 7.7 is in this 9 region. You see, this is the 10. 7.7 is the under the 10 region. So 10 is the some very severe. So we go to overview the monthly earthquake when on C the 28, 2025. Magnitude is 7.7. Epicenter is near Mandalay. So this is the northern east. So the depth is 10 kilometer. Effect is significant structural damage, casualties, and disruption. So when we see the movement magnitude of the depth earthquake, 7.7 earthquake is the, seismic movement is the in this amount, and then the magnitude is the 7.7 magnitude. So when we see the earthquake-related detailing, so then once we have the severe damage, we come to attention to the detailing. So earthquake-related detailing refer to construction practice that improve seismic resilience. So essential of our region, really essential for those kind of detailing. Those detailing can prevent catastrophic failure of building during earthquake. So type of damage during the earthquake: collapse of bridge and building, crack in reinforced concrete frame, failure of structure elements, poor performance of unreinforced masonry, like the Mandalay. In the Mandalay, the wall of the Asian wall has collapsed. So poor performance of unreinforced masonry. And as you see in the picture, so many buildings collapse, damage in the Mandalay region. So when we see this one, how severe is the lateral force of the earthquake? We can see, you see. So very severe lateral force when it is earthquake. So to cover this lateral force, we need the very precise earthquake detailing in the construction. So root cause of the damage is the inadequate detail in construction, lack of tactile reinforcement, poor quality control, ignoring code provisions, informal construction practice. These all 5 items, in my view, is the root cause of the damage during the Mandalay earthquake. So when we study the some picture, so why it's happened, you see, this one, failure column shear. The improper confinement of longitudinal bar led to shear failure column during earthquake. We need the very good confinement for the detailing so that we can prevent such kind of damage. Second is the open ground story. So the upper story is the brick wall and stiffer, but the ground floor less stiffer, so that failure of column because of poor energy dissipation capacity. So another one is when we study this one, we see weak column, strong beam. Beam is still okay, but column is gone already. So when we study this one, in my opinion, it is because of captic effect, because of architectural requirement, and then the column cannot withstand due to the captic effect. So when we study this steel frame, it is because of lateral force coming to the warping torsion. So we need the good stiffener in the steel structure. So come back to what is earthquake-related detailing. When we talk about detailing, we need to consider all those things: tactile design, proper startup spacing, beam column joint reinforcement, confinement reinforcement in column, ensure energy dissipation during quake, captic effect due to architectural requirement. All these 6 items have to be considered for the ductility of the structure. So, okay, when we go to see lateral force, you see, this is the gravity. When it is gravity, our beam is the behavior like this: positive movement, negative movement. Once the seismic lateral force coming, it change to this behavior, and right side, left side. When we see the resulting movement, we become like this, so that we need to treat the end condition. End condition and this condition have to be very good ductility to withstand the seismic. When we see the column, when lateral force come in, the behavior, moment behavior like this, so the left supply region is somewhere here. So this area come in the plastic hinge area, so that no supplies in this area. Okay, we go to study all the detailing of the reinforced concrete. This all is from our teacher. Saya ulang sang reference book. I am present from this one. Okay, so for the RC structure, according to GVC, we have the seismic zone 0-1 low, 2A, 2B moderate, and 3-4 high seismic risk. Mandalay is already considered zone 4, according to GVC. So in Myanmar, we have already considered all the seismic design concept already in place in Myanmar. So when we talk about moment resistant frame, we have 3: ordinary moment resistant frame for the low zone, intermediate moment resistant frame for the intermediate zone, special moment resistant for severe seismic zone. Because Mandalay is under the zone 4. Zone 4 here already designed, already in place, already take action already. So when we study the ordinary moment resistant frame, this is the gravity. So all the, there is no plastic hinge, so we can have the left supplies not in this region, not in this region, not in this region. This is the concept of the ordinary moment resistant frame. So if you want to left supply, it is outside this area. If you want to left supply outside this area, in the center, positive movement, you cannot be the left supplies. So beam, the same here, the same concept for the beam as well. For the column, the left supplies you can do in the after slab. After slab, you can do the left supplies in the region. So, and then the startup spacing also according to the code requirement of the 16 dB or smallest dimension of column section C1 or C2. So normally smallest dimension is okay. So this is the how to confinement for the column. But ordinary moment resistant frame, hook is still 90 degree. Then we go back to the intermediate moment resistant frame detailing. So when intermediate come in, there is the definition of plastic hinge region is come into concentration. So that the code define 2H area, 2H is the plastic hinge area. In this plastic hinge area, there is the no left supplies we can do. So, and then the spacing of the startup. Spacing also startup is the 8 smallest part diameter coming divide 4 or 12 inches for the intermediate. When we see the column for the intermediate, there is the plastic hinge area. In this area is defined by the larger of C1, C2 or clear height by this clear height by 6 or 18 inches. So in this area, no any left supplies is allowed for the intermediate moment resistant tray, and the hook is become the 135 seismic hook. So now after intermediate moment resistant frame, we become the special moment resistant frame. In special moment resistant frame, minimum 2 bar continuous. Here 2 bar continuous, here 2 bar continuous. You cannot supply in this zone for the definition. And plastic hinge area is the same as 2H, same as the intermediate moment resistant frame theory. So the spacing is become divide 4. During the intermediate, it is divide 4 and 12-inch minima. Here is divide 4, 8 dB is less already, and 12-inch minima. Then the hook is the seismic hooks. Everything is the same. So for the special movement resistant frame column, the same is the plastic hinge area is the same. Larger of C1 by C2 or clear half by 18 inches, but the spacing is the different already. Spacing is C1 by C2 by 4, 0.25, very small spacing we have to use for the special movement resistant frame. The startup spacing is become lesser compared with the intermediate movement resistant frame. It is 0.5 of C1, C2. C1, C2 by C2, C1 or C2 divided by 2, but special movement resistant frame, C1 or C2 divided by 4.25, because it's more confinement, arrangement of more confinement for the special movement resistant frame. Then, so for the RC structure, we advise follow MNBC, ACI, Eurocode. MNBC is Myanmar National Building Code. ACI, Eurocode standard, proper anchorage and left supplies, as I mentioned before, and shear detailing and confinement, detailing, improved ductility and resilience, proper management for captic effect. So that if you follow all these things, I think you can resist the earthquake lateral force around in some instance, you see. So for the RC structure for ductile delay, I recommend is the IS 139020 code and commentary, because why I recommend it is from the World Bank project. With the experiment, they define something better. So when we see the IS code, you see here, so response reduction factor, they change. In the gravity design, if we use 3, if ductile design, we use 5. So increase response reduction factor increase to minimize the risk of earthquake damage. So another interesting is the minimum width. Ordinary design not defined, but ductile design is the 200 millimeter for the beam. So then the startup spacing I had mentioned already. So from here, what we learn is the minimum dimension of the element is defined. So for the column also, but response reduction factor is the same, but the minimum dimension of the column become 300 millimeter. So this is the ductile design requirement. So we go to the next section. So up to now, what I present is the all RC structure. So now we go to the steel structure. Once we talk about the steel structure, we have to follow AISC seismic provision. So when we talk about detailing of the steel structure, so we cannot see only connection. But we have connection is less important in the steel structure. The more important is the material requirement, member and connection requirement, structure requirement. All these three together make it steel structure ductility. So when we talk about the stability, we have 3 equilibrium. 1 is stable equilibrium, 2 is unstable equilibrium, 3 is neutral equilibrium. When the low capacity reach stiffness 0, it's become the neutral equilibrium. When stiffness is negative, go down, it's become the unstable equilibrium and structural stability failure. So to protect this kind of condition, we need the ductile design of the steel structure. So what is the ductility? So when the material is tested, when it's go to shear, is going further before brittle failure is we call ductility. So if steel structure become like this, is no ductility, further go less ductility. If can go more further, more ductility. So then we study all three things: material requirement, member, structure. So this is that I recommend AISC. This is 2024 update. So go to the material. So what the AISC recommendation is, limit maximum yield stress 50 KSI. Why this limitation? When high strength material steel is high strength, less ductility. Therefore, we have to use A36. A572 is more better than A36. So this is the AISC limitation. We have to use yield strength not more than 50 KSI. Then use expected yield strength F1. We not use minimum Fy from the test. We have to use the Fy expected because factory manufacturer more strength than the what we define the minimum yield strength. That's why we have multiplied with the true strength factor. A56 1.3. So when material finish, we go to member requirement. When we use the tactile design of the structure, we have to use the compact section. So compact section is the not cylinder section. Compact is being controlled by the width and thickness ratio, B by D ratio. So we have to use the low B by D ratio and adequate lateral bracing. When we make the lateral bracing, we cannot use such kind of bracing. We have to use the member more than half of is high, you see. Then this lateral bracing is adequate. This is not adequate. So when we see the compact section, it can resist more movement than the cylinder member, cylinder element. And when we study this curve, so this is the width thickness ratio B by D. When it is low B by D, it's more ductility. Okay. When we see moment capacity, low B by D ratio have the more plastic moment capacity. So we have to select the member in this region. So we can get ductility of the element member. So in the structure requirement, we have 3 moment frame. So ordinary moment frame. So this joint design for 1.1. Why we overstrength factor, we use 1.1 to get the some instead of small earthquake, it can resist as well. So for the median ductility class, we have to use the intermediate moment resistant frame, which is the joint design is making 0.02 radian minimum. But this is the minimum, no? Maybe you can do 0.025 as well. So for the high class ductility, so we have to use 0.04 radian rotation for the joint. So this is all the requirement of ductility of the structure. So we study frame and superstructure. When we come to the substructure, there is the pile reinforcement recommendation for driven pile and press pile. Normally, when we have land from the side, you see, most of some side they neglect the pile head treatment. For example, so driven by press pile, we have the pile have to intrude to the footing around 150 millimeter is the best for the fixed connection. Some people keep it 75 millimeter, but 150 millimeter is complete fixed connection for ductility. Then rebar have to be go minimum 2D length inside the footing. Then you can get the fixed connection for the ductility. Otherwise, I'm not sure. For the pile foundation, ball pile foundation, we need the confinement, spiral reinforcement, transverse reinforcement in this area, point of inflation. This point of inflation we can find from soil structure interaction analysis from the pressure, PY curve pressure and deviation curve, you see. So in this region, we recommend to put the transverse reinforcement spacing less than or equal to 100 millimeter to make the confinement to resist the lateral force. So this is the, if you want to fix connection for the foundation with the structure, please pay attention to those requirements. So for the steel structure, I advise follow AISC strength limit. Ductile member shall be weakest in the load part. So if in the load part, if non-ductile member, you put in non-ductile member, then you have the structure problem. Provide connection stronger than member. So avoid high strength steel in ductile element. Use cross-section with low width and thickness ratio. Provide adequate bracing. So what we learn from Mandalay, so we see a lot of damage in the Mandalay after earthquake. So what we get the lesson, we need to follow the code compliance. So we need to follow the code. Need for skilled professional, and we need to check during the construction whether the design requirement is properly in place or not. Another one is retrofitting and maintenance. So we have to study the existing building, whether it is retrofitting or not. You have to check regularly. Risk of informal construction. This one, we study a lot in Mandalay, informal construction practice in Mandalay. So when we study the Mandalay, properly detailed structure, minor damage, no damage, properly detailed like the building construct under the high-rise public committee, HPPC, there is the small minor damage, but poorly detailed structure, severe damage or collapse. So detailing improve performance significantly. So what my recommendation is the enforced seismic design code for the construction industry. Train foreman, engineer, architect, and worker about the importance of ductility and detailing. Retrofit vulnerable structure. So conduct public awareness campaign. So this is very, difficult job for the engineer. So, what we have to tell them, awareness, lack of permit and inspection is not good. So hiring unskilled, uncertified worker is not good. Using substandard material is not good. Inadequate foundation system is dangerous. Unpermitted extension should not be done because of the overloading the original structure, and it is dangerous. Lack of material testing, what they are using is good material or not, is also another important matter. Another one is the absence of engineering design. So all those things we have to be tell the public, these all are dangerous for your building. So, but on the other hand, poverty and affordability is blocking all these things. Lack of access to formal service. So like the difficult permitting process and block this all thing. Another one, traditional construction method. They don't want to change traditional construction method. Block all those things again. So lack of awareness for long-term risk. So they see the financial for the present construction time, but they are lack of awareness for long-term risk. All those things block this item. So in the conclusion, earthquake detailing is critical for safety. Monthly earthquake highlight the need for some correction. Structure safety equal to ductile design plus detailing plus supervision plus enforcement. If you do all, you get the structure safety. So for the ASEAN matter, for the cross-border engineering service among ASEAN countries, we need ASEAN occupational standard for construction. Like we need the one standard for the all ASEAN countries. Which code we are going to apply? That we have to further discuss for this matter. And for the localized, for the local practices awareness training on construction compliance for the foreign worker and foremen. Once we cross border already, we reach to those country people, have to do the awareness training course for the all foreign worker and women, so that to get their safety. So thank you very much for your kind attention, all of you. So if you have any question, I'm happy to answer from here.
Okay, thank you so much, Dr. Somian. Actually, I really love your comprehensive recommendation from various perspectives about this issue, these serious issues. But you also have mentioned about lesson from Mandalay, right?
Yes.
So I would like to ask whether, how about the lesson from Bangkok, in your opinion, because you are here for a long while, okay? And I'm sure that you have followed and observed the news, the media about this incident. What's your personal opinion about this collapse?
Yeah, this is very tough question. Anyway, so as an engineer, I have something in my thinking as well. You see, when we study Thailand, so in terms of design, Thailand is more advanced already in the design. So very good design for high-rise infrastructure. Even we involved in all those design. So we understand in design very good enough already. So, but for the earthquake, so we have some crack on the building. So you need to little bit upgrade for the design in terms of seismic requirement, like the PGA. Like the PGA for the Bangkok, you have to modify a little bit. So then design requirement is not much. In terms of workmanship, okay, so now during this time, a lot of foreign workers working in Thailand, you see. So there is Chinese worker from the ASEAN people, so Cambodia, Laos, Myanmar, all they are working. So that I'm not sure Thailand is making the construction compliance awareness training or not. So this is what I recommend, because each country have their traditional construction method. So if you not make the awareness training, if they come to put their traditional construction practice, then it's also the problem area, you see.
I see.
So this is my two things. For the collapse, okay, this is design and construction.
Of course.
For when I see the collapse, so collapse is under construction building. Completed building, there is no collapse, no collapse, because there is the perfect frame already.
Yeah.
So for the collapse building, I recommend ETAP, or you use Step Pro, whatever it is. ETAP program running needed before construction finish, like the skeleton. So you need the under construction, what will happen? So once you see the ETAP program, then you have to put additional member or not. I mean, this is my very, recommendation, very severe recommendation to them, not put it, the ETAP program designer, complete stage. During the construction stage, you have to run.
I see.
Okay, this is the one recommendation.
Okay. Thank you.
Yeah.
And before we enter this panel discussion, I think we have a chit chat, and Dr. Somian also mentioned one very interesting point about you have mentioned about the standard already. The design and construction standard is not bad. Let's say like that. But anyway, since this incident really shocking a lot of Thai people, okay, and the public really pressure the government and all relevant authority to enhance or improve the standard level in terms of seismic resistance.
Yes.
What would be your opinion about this?
Since when we study the Bangkok, you see my second slide a little bit decreased bit. Oh, it's okay.
No, yeah.
So for the seismic, there is the Quanchai, 1996.
Okay.
There is his study about PGA.
Okay.
It's 0.02, something like this. But later on, other people is the 0.15 to 0.26 5 or 269, I don't remember.
Yeah.
So, I mean, this is something okay, but I'm not sure the seismic map of the Thailand, Bangkok,
Right.
is the still MMI scale 1 to 5.
Mhm.
This is have to be revised. Okay, MMI scale
see.
1 to 5 is not enough based on this monthly earthquake.
Okay.
So you have to revise your seismic map.
I see.
So I recommend around 0.2 to 0.3. Something like 0.2 is the better. 0.2 to up to you. 0.15 to 0.3 I recommend.
Right.
So you have to consider this thing and
Okay.
revise the map. Okay.
Okay, thank you. But since this incident really unique because only one building under construction collapsed. But if all the engineering societies in Thailand really need to change something, to modify something to ensure that it will be safer in the future, how do you think about in terms of the budget spending?
Yes.
If
So-
the country, the nation really need to improve this, but need to spend a lot of
So,
money for it, do
yes,
you
I
think it's
want to-
worthwhile? Yeah.
I want to express one word. How good is good enough? Yeah, how good is good enough? As an engineer, we cannot do very good, you see.
Right.
We have to consider the financial thing, you see. If you increase PGA,
Right.
when you have to check the liquefaction, this is a lot of liquefaction coming. You have
Okay.
to put all your money to the ground. So this also we not appreciate. Okay? So, I mean, acceptable damage, you have to define. Suppose now many Bangkok buildings have the crack.
Right.
It is acceptable or not? If not acceptable, you increase little bit. But in term of earthquake, we cannot total control. This is impossible total control. You have to put the some damage, 20% damage, and based on this, with the previous your design and your damage control system, how much you have to improve? I mean, little bit is, my opinion, enough already. No need to increase too much. You see how good is good enough?
Okay.
Not total damage control is impossible in the
Yeah.
earthquake. Yeah.
Okay, very good point. Thailand is also not a very rich country, right? So we still need to consider from all perspectives.
No, rich or not rich. So we should be or should not be. It's
Right.
the more important in the engineering sense.
Yeah,
Yes.
absolutely agree with you. Okay, thank you, Dr. Somian. I need to pass the floor to Dr. Imran, who's with us for a while, but I intend to give you as a last person for this presentation because I know that you are traveling, right, from Bandung to Jakarta. Just arrived in Jakarta. So I hope, you are now okay. Okay. Then, yeah, since you also structural engineer, as Professor Sengara also mentioned about that. So you may have something to add to what Dr. Somian has mentioned as well. And of course, your presentation talking about improving the seismic resilience. Yeah, please, now the floor is yours, Professor
Yeah,
Imran.
thank you, Chairman. Yeah, aside from Bandung Institut Teknologi, I also with the Institution of Engineer of Indonesia and also with the National Center for Earthquake Studies. Yeah, actually, some of my presentation already been mentioned by Dr. Sengara, Professor Sengara. So probably I skip some of them during my presentation. Yeah. Yeah, I think Prof. Sengara already mentioned this. A lot of significant number of earthquake, yeah, around Indonesia. When you ask Prof. Sengara about Bromo, yeah, he mentioned about the southern part of Java. Yeah, you can see the southern part of Java. There is a lot of seismic records. Yeah, this is the seismic record for the last 100 years. Yeah. With the magnitude from 4 to 9, yeah, and then some of the magnitude there is greater than 7 actually, which is a very damaging earthquake, yeah, for us. Yeah, every time big and damaging earthquake occurs, many buildings and infrastructures experience heavy damage and sometimes collapse, yeah, as shown in this slide. This is due to 2018 Palu earthquake, one of the largest that we experienced, because this is a earthquake in the land, the source. And also one of the bridge there, this is a landmark bridge actually in Palu City, also collapsed due to the 2018 Palu earthquake. To reduce the earthquake disaster, some mitigation strategy already developed in our country. These are the list. Just some of the list actually. Some of these already mentioned by Prof. Sengara. So I only touch some or probably add the one that has not been mentioned by Prof. Sengara. The first one is conducting reconnaissance studies to obtain lesson learned from every seismic event. Prof. Sengara mentioned this also, and we frequently, every time after the earthquake, we form the team to study the area, to study the damage, to get the lesson learned from what happened there. The last report that we produced is in 2022. This is a Cianjur earthquake in West Java, actually nearby Bandung. So this is quite damaging as well. Many buildings experience major damage due to this earthquake. Again, we try to get many lessons learned from all this earthquake event. Pak Wayan mentioned also about continuing updating seismic hazard map. This is the evolution of the seismic hazard map of Indonesia, started from 1966, and the current one is 2017. But now we are on the process, on the final stage to issue the updated seismic hazard map of 2024. So every time it is updated, the numbers of active fault lines being considered keep increasing. This is because we have more data, more data available. So that's why it is considered in the development of the updated seismic hazard map. So in 2010, we have only 81 active fault line. In 2017, 295, almost 3 times. More than 3 times, I mean. And then in 2024, 402 active fault line. Now, with this increase in number of fault line to be considered, of course, there will be an increase in the seismic hazard level that we have to consider, for the seismic hazard map. And every time we have that kind of situation, our concern is the existing buildings. There are always some vulnerability, already there in the existing building. At least, the base shear capacity of the building, especially those designed based on the older seismic code, much lower than those designed based on the current code. And the other important thing is that the existing seismic detailing may not be adequate for area with the increased seismicity, especially to anticipate the unexpected. I think this is also support what the previous presenter mentioned, the importance of the detailing. The seismic detailing actually based on the seismic design category. The seismic design category will be based on the acceleration in the area. Once the acceleration increasing, the seismic design category will also increase. And as a result, the detailing requirement will also increase. Now, that's going to be a concern for the old or existing building. These are other source of vulnerability recorded, from the observation we did, in Indonesia. Always some inconsistency sometimes, between design and construction. And seismic demand is also sometimes higher due to many factors, such as irregularity, unisolated non-structural component, excessive mass, yeah, etc. I think some of this mentioned also by the previous presenter. Seismic detailing requirement, yeah, in Indonesia is also sometimes not implemented consistently. Yeah, sometimes the designer use higher R values, the response modification factor, yeah, higher values, but then the detailing is just ordinary. Yeah, so that's of course mismatch. Yeah, will cause some vulnerability, yeah, to the building. Yeah, this is the example. Yeah, after the earthquake, of course. Yeah, we can observe a lot of deficiency and vulnerability, yeah, of one of the detailing, for example, in the beam column joint. Yeah, you can see there not enough confinement, yeah, in the joint, yeah, and as a result, due to the earthquake, the joint experience significant damage, yeah, and sometimes cause the collapse of the building. Yeah. Now, because of this concern, yeah, existing building, yeah, need to be evaluated seismically. Yeah, the purpose, of course, to mitigate risk of collapse of existing building due to the earthquake, especially those designed based on older code. In Indonesia, it is also related to the requirement for function worthiness certificate or SLF of building structures. Yeah, it is actually mentioned in the regulation of our government. And recently, our government issued this SNI, Indonesian National Standard, yeah, for seismic evaluation and retrofit of existing building. Yeah. So this code actually basically performance-based code. Yeah. So even though the structure has some deficiency, for example, as long as the performance can meet, yeah, the requirement, then it is fine. If it cannot meet the requirement, then of course you have to do some retrofitting. Yeah, the next one is regular updating of relevant code and standard. Yeah, our seismic code for building design, yeah, actually comprise of code for determining seismic load demand. Yeah, this is we call the SNI 1726. We adopt actually the ASCE 7. Yeah, I think similar to what I think I forgot the name, the presenter before, that in Bangkok, in Thailand, they also use ASCE 7 as the reference, yeah, for the seismic codes. Yeah, so the same in our case. And then for the detailing, yeah, the second code needed for the design, yeah, we follow the AIC, yeah, the same like the one mentioned, yeah, for the Myanmar, for the steel structures, and then ACI 318, yeah, for the concrete. So as long as we implement these two codes, yeah, consistently, then of course, yeah, I agree with the previous presenter. We will get a building that can survive the earthquake. Yeah, yeah. This is just information of the codes that we have. Yeah. Yeah, the next one is applying state-of-the-art technology to reduce seismic demand. This can be implemented for the existing building and also for the new building. Yeah, but so far in Indonesia, we only apply to new building. Yeah, some of them actually existing building as well. Yeah, but so far, as far as I remember, only one building, existing building, that has been retrofitting, yeah, using anti-seismic technology, yeah, or anti-seismic device. Yeah, there are two approaches that usually implemented here in Indonesia. One is to isolate the upper structure from strong ground motion using base isolation. Yeah, the second approach is using special seismic dampers. Yeah, usually we use the passive dampers, yeah, for this purpose. And some of the device, for example, lead rubber bearing, yeah, are now already produced domestically in Indonesia. So this device has been implemented in many projects especially for the elevated structures like bridges. Some of the bridges in Jakarta, for example, elevated structures there already equipped with this device, seismic device, anti-seismic device, I mean. Yeah, the next one is implementation of government regulation to control building permit. I guess Prof. Sengara already mentioned this. We have we call it building advisory committee for high-rise building. So all the design has to go through this review process in this committee. And then we also have bridge safety committee. I think Prof. Wayan, Prof. Sengara didn't mention about this. Our government also set up a bridge safety committee. Similar role actually. Expected during the construction and also the design, in order to make sure that all the design process already according to the standard or the codes that we have. The last one, our government also has a program to develop risk map for all cities and regency in Indonesia. These are the example, some of the map. This is actually the vulnerability map of Jakarta. So Prof. Sengara mentioned about the fragility curve that he has developed. We use that curve then to identify or to develop the vulnerability map in Jakarta. Based on that, we can also develop the risk map. Like the one shown here. So this is the seismic risk map of some part of Jakarta. One in Cipayung district and the other there in the Duren Sawit district. So based on this, we can know the risk of the buildings or the housing in the area. I think that's all that I want to present. Thank you. I cannot hear your sound, your voice. Okay.
Fix it now. Okay. Can you hear me now?
Yes.
Okay. Thank you very much for your presentation. Actually, you have added to this topic very well, because you mentioned about the infrastructure project, which recently the issue in Thailand is only one building collapse. Okay, but anyway, there are so many other buildings and infrastructure damage as well. So this is something we have to learn from Indonesia, that you have so much more experience than us. Okay. So my question to you may be, in case of Indonesia, I'm sure that you have been going through this kind of issue in your country. How frequent that you need to modify your design code in terms of accommodating this seismic resistance? Is there any major change from the history? Any statistic about it?
Actually, in the last 2 decades, the seismic hazard map of Indonesia is always updated every 7 years.
7 years, I see.
Prof. Sengara mentioned before that one of the biggest earthquake we ever experienced here in Indonesia, which is the Aceh 2004, that kind of wake us up. That's why we try then to understand our country. We try to understand all the potential fault line surrounding us. That's why, as I mentioned in my presentation, the number now keep increasing. Because the research is still going on up till now.
Okay.
Not only the research, but also the earthquake. The new earthquake not the new earthquake, the earthquake that originated from the place that has not been recognized before. So that also occur many times, like the one in 2002 to 2022 in Cianjur. Yeah, we never expect that the location, the epicenter of that earthquake is in that location.
Okay.
It has not been recognized before. So that's why the increase of the fault line keep increasing. Yeah. In 2010 seismic hazard map, we only have 89 something, but then in 2017 up to 295. Yeah.
I see.
That's for the fault line, active fault line. And then the recent one, the one that I mentioned in the final stage of process, yeah, probably within this year it will be issued, yeah, the new seismic hazard map of Indonesia 2024, total around 402 active fault line. Yeah.
Okay.
And now every time we got new seismic hazard map, then of course we have to modify our code, our respective standard.
I see.
Yeah, because this map will be accommodated in the seismic standard later on.
Okay. Very interesting information, because we all know that the earthquake is act of God, right? But it looks like nobody can really forecast or foresee it accurately. So as you mentioned, that many times it happened to the area that we never recognized before. So even country like Thailand, we still need to be vigilant about what could happen to this kind of disaster. Okay, so yeah, thank you for your information. In fact, I have a lot of questions from the participant lineup, but I really need to beat the time because we have very limited time, let's say 10 to 15 minutes from now. So in this case, I intend to show all the questions, right, on the screen. Okay, so all the panelists or three speakers, if you look at it and you really want to answer, to help answer certain questions, please feel free to do so. Otherwise, I will go through one by one, or I will try to make it selective. Okay. The first one is major differences in earthquake resistance standard among Asian countries. What do you think about this? Any of you?
Well, I think as the previous presenter also mentioned, yeah, from Myanmar and Thailand, yeah, they mostly use like for the seismic loading code, yeah, they use ASCE 7, and then for the detailing refer to the AIC for the steel structures, and then ACI, yeah, for the concrete structures. So it seems not much difference, yeah, between the countries. Probably the only difference is the version of the code being referred to. Like for example, for the Thailand, if I'm not mistaken, yeah, it's mentioned refer to the ASCE 7 2005 or 2002. In our case, we refer to ASCE 7 2016. So probably just the difference in the version.
Okay. How about you, Professor Sengara? Do you want to add anything?
Yeah. I think one thing that we in Indonesia like to follow the most recent international building code, particularly the MSCE 716. So there is a conceptually different spectra, this design spectra that we put into the buildings, what we call risk-targeted ground motion, risk-targeted spectra, which is actually modification of the hazard map. We call it risk. Yeah, we call it risk-based map.
One more important. Okay, then you have to make very brief then. Yeah.
Sorry. Yeah, we call it a risk-based hazard map because it's different than conventional hazard map that we use, and the SCE 7 2005 is It's different than the concept of providing design spectra for the ICE 7 2016. And somehow we are fortunate, we already adopt the risk targeted ground motion, which is, I think, not many countries adopt this yet. So that's my additional response to that.
Okay, thank you very much. And couple more questions that's specifically for Dr. Somian. Yeah, would you like to share question number 9 or 10? Yeah,
10,
the 10 one. For welding of seismic structure, we need to apply AWS D1.8 or not?
Yeah, for the steel structure, there is the AWS D1.1 and D1.8. 1.1 is static and cyclic load. D1.8 is there for the seismic structure purpose. Yes, you can. Yes.
Okay.
This is the answer.
How about number 9?
Number 9, can you show me the slide again? 5 point, stated lesson learned.
The lesson learned one.
5 point. So I have to see the.
Okay.
Yeah, 5 point lesson learned. Concrete, under the concrete section. Go further.
Up. Go up. Or down.
Oh, up. So this is the structure. 5 point lesson learned. Yeah. This is this slide.
The lesson learned.
Lesson learned. Up.
Lesson learned Mandalay.
Yeah. Lesson learned Mandalay. Up.
No, down. Down. Scroll down. Scroll down. Yes, correct.
Down.
One more slide. Okay, is this the one? Okay, leave it here. Yeah.
So that's the importance of compliance. So I mean, in Mandalay, you see, some people not follow our MNBC code and regulation issued by the MNDC, YCDC, or HPPC, you see. So I mean, for example, what the material, what the reinforcement they got, they use it without testing, without verifying the code compliance or not. I mean, this one. Need for skilled professional. So I mean, so for the ductile connection, we need the standard spacing have to be horizontal or vertically exactly, you see. So to check all these things, we need the skilled professional to stand by during the construction. So he go outside and worker doing concreting already. So he have no chance to, inspect it. That's why we need the skilled professional. Retrofitting and maintenance. This is only for why I don't know. Okay, retrofitting and maintenance. So you have to check all the existing building, which is the requirement to correct deficiency for the seismic design. You need to make the retrofitting and maintenance accordingly after structure run ETAP.
Right.
Risk of informal construction. So you have to, educate the people. Informal construction is very dangerous for your project, for your building. So please follow formal construction procedure.
Okay.
So this is what my intention.
Yeah, thank you. Since it's in Dr. Somian's slide, we can share the slide to all the audience later through email. Yeah, that's not a problem. Okay, we'll go back to the question again, and probably we have only 5 or 10 minutes left, and that's why question, please. Okay. Shear wall question. Which one is that? Scroll up, please. Scroll up, please. You have seen it, right?
No. Where?
Or down?
Send me here. Have the shear wall question.
Never mind, then you can answer to that question. Okay. And while Dr. Somian finding that question, searching for it now, I would like to ask the very final question for all 3 panelists to answer at the very end of this session. Okay.
So I got the
okay, Dr. Somian, ready to answer this question now. Go ahead.
So the question is, I have a question. In the case of earthquake-resistant building, the minimum thickness requirement for column according to ACI is not less than 30 centimeter. How about there is not such specific requirement for shear wall? Should we consider revising, improving this aspect? For the shear wall, shear wall normally, I mean the thickness is 15 centimeter to 40 centimeter, you see. For we just follow this one because shear wall is based on according to building height. But then the earthquake intensity,
อ๋อนะพร้อมแล้ว
shear wall earthquake intensity, building height, and the material used. So that structure engineer will define the thickness of the shear wall. Hope this is the answer to the question.
Okay. Yeah. Thank you, Dr. Samir. Yeah. I truly apologize to all the participants because we very limited of time. So this probably really the final question to all three speakers. And of course, since this topic really Thailand really wait and see whether what would be the investigation report will be reviewed next week or so. Okay. But in terms of your own experience, no matter by statistic, by your study, or even personal opinion, what do you think normally would be the major cause of building collapse or infrastructure damage in your personal opinion? Yeah, I want to hear from all speakers, please.
One by one.
Or even one word, if you like. Yeah. Dr. Sengara first, in order.
Okay. Yeah, thank you. This is actually from what we are discussing. So this is the building collapse is related to the the resistance of the structures and also the hazard that come, the event, the earthquake event that subject the structure. So one of the cause of the building damage or building collapse is I think it's whether the design spectra for the building is actually match the smaller or lower compared to the spectra or the ground motion that occurred during the earthquake. So if it is higher, then the building can resist further, and some damage or even collapse could be resulted. So this is related to the hazard map. So in Indonesia, for example, in some of our earthquake occurrence, somehow we find out that the hazard, the earthquake hazard, is higher compared to what the design, the building is designed for, the spectra, particularly for the for the for the previous older buildings. So this is exactly in fact we identify in 2009 earthquake in Padang city. We identify many of the building collapse. The older version of the codes house many building collapse because of the the spectra or the ground motion is we identify higher compared to the codes used from the previous codes. So that is one of the causes. So that's why in our case we keep updating the hazard map and also the building.
Yeah.
The second one I think is particularly on the structure itself, whether the requirement, the code standard has been satisfied, is complied with the codes, the detailing and so forth. So many structural aspect I think is related to that. I think Professor Imran and also Dr. Min, I think more expert on that to explain that. And of course, the compliance of the code is also important. The building authority through the evaluation process, like what I have mentioned in the presentation, is one of the critical item. And the third one, I think of course, the building supervision. So you design your building good, but if the construction is not according to the design, and then you have a risk, you create a vulnerable construction.
Okay, thank you very much, Dr. Sengara. Dr. Imran, yeah, next, please. Yeah.
Okay, thank you. In my opinion, even though the seismic demand is a bit higher, for example, compared to the base shear strength of the structures, the structure will not collapse as long as detailing is there.
Okay.
So from what I know, Bangkok, most of the seismic design category there is not SDCC. It's not SDCD, but SDCC. So with the C, you can apply sometimes just ordinary detailing or intermediate at most, not the special one. One of the parameters that affect whether your building will be in the seismic design category C or D is the spectral values at 1 second.
Mm-hmm.
The spectral value at 1 second in Bangkok, the number is 0.199. Yeah, please correct me if I'm wrong. That's in the code. 0.199. The borderline to enter to seismic design category D is 0.200. So if you are in the 0.200, your SD1 or the spectral value at 1 second, then automatically you have to design your structure with special detailing. Yeah, because you are now in the seismic design category D. So once you do that, you can anticipate the unexpected. What are the unexpected? Higher demand of the earthquake, some problem in the construction, for example. But if you don't have that detailing, once you have some weakness, either from the external cause, the higher demand, or from the internal cause, then you don't have any like reserve capacity or reserve. I mean, like you cannot redistribute your load easily because you don't have the detailing there. So that's my opinion. Thank you.
Okay, thank you very much, Professor Imran. Next, Dr. Somyan, please.
Yeah, when we look at the, slow motion of the collapse building, we find the busting of the column at the exterior column, left side, and collapse from the right side coming like this in stable. So when we study this one, according to my presentation slides, so material also another important factor, you see. If material is cannot tactile, so ductility cannot achieve it, then it also the problem. Once the force come in, it cannot resist anymore. On the second matter, during the construction, there is no temporary shoring. So once the external torsion come in, it cannot resist alone. The column alone cannot resist for the height of the building, you see. So I think my opinion is for two things. One is the material is not tactile enough to resist it. Second is not have the temporary shoring. So as I explained before, you need temporary shoring by ETAP modeling during construction. This is my opinion. Why happen? Maybe two things. Yeah, maybe wrong or right. I don't know. That's my opinion.
Of course. Yeah, as I mentioned, also Dr. Quanchai mentioned that we will know the result from the investigation team very soon, and then we will review to you all in the next opportunity. Then. Okay. So before I pass the forum to Dr. Quanchai to have his closing speech to us on behalf of the moderator of this panel discussion, I really thank all three panelists who have been with us from the beginning, Dr. Sengara, Dr. Imran, and also Dr. Somyan. Okay. And from what I know, today is also Islamic New Year, right?
Yeah.
So happy Islamic New Year to all Muslim friends.
Yeah.
Okay.
Thank you.
And hopefully we'll meet again in the Thailand ACPE Forum number 3 very soon. Okay. So in this time, I would like to invite Dr. Quanchai to give us the closing speech. Thank you very much. And Dr. Quanchai will be saying the final word with you all.
Delegates, our colleagues from, I think, 11 or 12 countries this afternoon. I've been with you all along 3 hours with interesting topics that presented and also the first fruitful discussion. I think today we know quite a lot of things. And your experiences have been shared and also knowledge been shared among us, among our ASEAN countries. Today we turn sorrows into strength. And we talk about safer designs to save more life. And this incident from Myanmar to Bangkok is actually unbelievable. Only one building's collapse in Bangkok among another 200 construction sites. This is very interesting. I'd like to share with you my concluding remarks. From our sharing and discussion today, this afternoon, it is clear that the disasters are becoming more frequent and more severe, like the deputy governors said this morning. Our ASEAN countries, we must prepare ourselves to cope with that reality. We cannot be away from that truth. We need to share more knowledge, experiences, and lessons learned among our countries, both in ASEAN and also our partners like Japan and other countries having the same threat, the same problems. We need to improve our codes, our standards and practices to reduce disaster risks and save more life. We strongly encourage our ASEAN member states to continue this valuable exchange by hosting this open forum like this in turn on a rotating basis. The next ACPE forums may be hosted by our friends like Indonesia, Philippines, or Myanmar. I think we may also propose to establish a more permanent ASEAN working group. This is my idea on earthquake disaster risk reduction to explore ways to improve or to develop our ASEAN directives, codes, or even the common technical guideline, for example. And this is my proposal. And this is, I think, the conclusion from this forum this afternoon. By the end of this month, probably the next Monday, the result from the investigation would be reviewed. And we would publicly inform inform the findings from the investigation team set up by the government. So by the next Monday, the real truth behind what happened will be informed, will be known to everyone publicly. Finally, on the behalf of the Council of Engineers Thailand, we thank you for your participation and wish you all the safe trip back home, and look forward to seeing you again in the next ACP forum, either hosted by Thailand or other friends. Thank you very much. Thank you.